Hello students, your COMEDK 2024 exam is there. So in this video, we'll be doing a complete revision of the total physical chemistry. So I'll be discussing all the important topics, important subtopics, important formulas and the type of questions that will be asked from this. So from this particular video, you can easily expect 18 to 20 MCQs or more than that because the syllabus in physical chemistry is reduced. So number of questions might increase. So around 20 to 25 also you can say MCQs you can expect. So please watch this video completely, note down all the important formulas, all the important concepts and then revise them and before going to the exam. Okay, so let us start with this video. Please watch it completely. So first one is we'll see what all chapters are there. So the chapter is solutions, the most important topic. Then we have electrochemistry, chemical kinetics, thermodynamics, equilibrium, some basic concepts of chemistry and structure of atom. So we will not be discussing the complete chapter. We'll be discussing the key areas, the key concepts that you must revise at this last one day, right? Okay. So let us start here. First is chapter 1, solutions. So what are the topics in chapter solutions chapter? Solutions and its types, concentration terms, Henry's law, Raoult's law, ideal and non-ideal solutions, colligative properties and Van 't Hoff factors. Okay, quickly we will see them. So first is your type solution and its types. The first category is based on the solvent. So if solvent is solid, then it is called solid solutions. Solvent is liquid, we call it liquid solution. Solvent is gas, we call it gaseous solution. And then based on composition, we have homogeneous and heterogeneous solutions. So what you have to do, you have to learn examples for each of them. Okay. Now coming to the most important topic, that is your molarity. Concentration term, number of moles of the solute by volume of the solution in ml into 1000. How to calculate number of moles? Given mass of the solute by molar mass of the solute. Okay, please quickly have to write down all the formulas with me. Okay, now coming to molality. Molality is number of moles of solute by mass of the solvent into 1000. Right. Next is mole fraction. So mole fraction is number of moles of the particular component divided by the total number of moles. Okay. Now here, suppose there are two components, you know one more relation, XA plus XB is equal to 1. Okay. So now we have written 4 formulas. Okay. Now, so just keep a count of the formulas. How many, like when you revise, we have 1, 2, 3 and then 4th formula. Henry's law. So what does statement? You need not remember at this point of time. Just you have to know that the amount of gas that is dissolved in a liquid is directly proportional to the partial pressure of the gas, of that gas above the liquid. The expression is very important. P of the gas is equal to kH into mole fraction of the gas. Formula number 5. Okay. Next, what is there here? P is the partial pressure, kH is the Henry's constant, X of the gas is the mole fraction. Now, one more thing that you have to remember is solubility. Okay. Solubility is inversely proportional to kH value. More is the kH value, less will be the solubility. Okay. Now, coming to the next one. We have Raoult's law. Okay, so Raoult's law statement also here, that is not very important. Just you have to know that the vapor pressure of each component of the solution is directly proportional to its mole fraction. Just write down this much: vapor pressure proportional to mole fraction. 2 words. Okay. Now what you can see, or you can just write in the terms of formula, P1 is equal to proportional to X1. Now formula for calculating the total pressure, right? So this is your formula number. We have 6, right? We wrote 6. So this is formula number 7, right? P total is equal to PAXA plus P2X2. So where P1 is the partial pressure of first component. P total is equal to P0AXA plus P0BXB. What is P0A? What is P0B? P0A is the pressure of pure component. P0B is the pure pressure of component B. Okay, so these two values XA and XB are their mole fraction, right? Now here one more formula we will add, that is the mole fraction in the vapor phase, right? YA and YB. So YA you write down PA by P total and YB is equal to PB by P total, right? So complete 8 formulas from solutions now till now written. Now let us go to the next one. Ideal and non-ideal solutions. This is very important, students. Questions are asked from here. Graphs are given about the interactions they are asking. Okay. So you have to remember they obey Raoult's law, does not obey Raoult's law. Delta H mix is equal to 0, not equal to 0. V mix equal to 0, not equal to 0. This point is very important. AB interactions is equal to AA and BB interactions. Here AB interactions is not equal to AA and BB interactions. Quickly you have to note them, like remember this one. Next we'll go to, in non-ideal solutions, what happens? There is two type of deviation, positive deviation and negative deviation. These points are also very, very important. So first, in positive deviation, AB interactions are weaker than AA BB interaction. Here AB interactions are stronger than AA BB interaction, right? Now if you see the total pressure is equal, greater than P1 x1 plus P2 x2, here the total pressure is less. Now positive deviation, delta H mix is greater than 0, delta H mix is less than 0. V mix is greater than 0, V mix is less than 0. Okay. Now you can just see the graph for here. In positive deviation, graph will be towards the towards top, and then negative deviation graph will be depressed. Okay. Okay. Now coming to azeotropic mixture. So what is azeotropic mixture? Just definition you should know, that they have the same composition in the liquid and vapor phase. Only I have to write this much statement, same composition in liquid and vapor phase. Now they boil at a constant temperature. Okay. Now this is also of two types, maximum boiling azeotrope and minimum boiling azeotrope. So maximum boiling azeotrope, what is there? They show positive deviation. So those who are having positive deviation, they will have maximum boiling azeotrope. Okay. And one second, the solutions, okay, sorry, this is wrong. When there is negative deviation, okay, if there is negative deviation, then there will be maximum boiling azeotrope. You can see the examples here. And then for minimum boiling azeotrope, there will be positive deviation. Okay. So please change this one. Okay. Minimum boiling azeotrope will have positive deviation. Now examples you have to remember. Examples are very important. Now coming to the next one, colligative properties. So if you see, first one is, what is colligative properties? The properties of the solvent which depends on the amount of solute added. Okay. So now what is our first colligative property? That is relative lowering of vapor pressure. What is the formula for here? Only formula we'll remember. What is the concept? When a non-volatile solute is added, the vapor pressure decreases. So we have the formula delta P by P is equal to P naught minus P by P naught is equal to XB. Okay. Right. So we can write the formula once again here. Delta P by P, that is P naught by P naught is equal to XB. Okay. I think this is 9th formula. Okay. Formula number 9. So here what is P naught? Pressure of the pure solvent. What is P? Pressure of the solution, that is after adding solute what pressure has become, and XB is the mole fraction. Right. You can easily calculate this one. Next we'll go to the next formula, that is formula number 10. Elevation in boiling point, delta TB is equal to KB into M. So here questions are asked, delta TB is equal to KB into W2, molality formula we can write, into 1000 by W1, right? So in this what happens, M2 questions, most of the time you will find M2 is asked in the question. Okay, that formula we can use. Then next one, if we see depression in freezing point, so this is your formula number 11, same formula, delta TF is equal to KF into M. Now coming to your osmotic pressure, that is pi is equal to CRT, where C is the molarity, R is the gas constant, 0.0821 liter ATM mole inverse Kelvin inverse. Okay, and then T is the temperature. Now this is very important term. Two solutions having the same osmotic pressure are called as isotonic solution. So you have to remember what is an isotonic solution. Okay. Now coming to next question, next topic, that is your Van 't Hoff factor. So this Van 't Hoff factor can be like association and dissociation. From here many questions are asked, like they will be giving you solutions, like 4 options are given, which is having the maximum boiling point, which is having the minimum boiling point, or which is having highest osmotic pressure, relative lowering of vapor pressure. So you should be able to calculate the value of I, right? So I means number of ions dissociating. Okay. So for example, Na3PO4 is there. What will be the I value here? 3 ions from here, 1, so I value will be 4. So whose I value will be more? There the freezing point will be, boiling point will be maximum, right? So we can do in this way. Now there is also to calculate the degree of association and degree of dissociation. So one second, we'll see here 12th formula, this is 13th and this is 14th. So degree of association is alpha is equal to I minus 1 by n minus 1, and for degree of association alpha is equal to I minus 1 by n minus 1. Okay. So now we are done with the physical solutions chapter. So how many formulas we saw in solutions chapter? We got total 14 formulas. Okay, very easy formulas. So just revise them. Do some numericals from this. So you can do our top 30 questions from the solutions chapter. Do them once and then you will be completely ready for this chapter. Any question come, you can easily attempt. Calculator is also there. So there's no problem of getting wrong answers in calculation. The only thing you need to know is the concepts and the correct formulas, right? Okay. So now let us go to the next important chapter, that is electrochemistry. So this chapter is little difficult, people think, but your questions are asked very easy and from some specific topics only. You did not have to do all the things, right? So let us first quickly see type of cells are there, conductance is there, and commercial batteries are there. Okay. Now if you see in type of cell, we have two types of cell. One is your galvanic cell and another is your electrochemical cell. Galvanic cell, what does it do? Chemical energy to electrical energy, and it is a spontaneous process. Electrochemical cell just converts electrical energy to chemical energy and it is a non-spontaneous process. Okay, nothing to questions will not be asked from here. We'll go to galvanic cells. So what are the topics under galvanic cell? We have working of a Daniell cell, cell notation, electrode potential, cell potential, Nernst equation, equilibrium constant, and relation between delta E and delta G. So here questions are asked from Nernst equation, equilibrium constant, delta and delta G, and then we have cell notation, electrode potential measurement. Okay, these are the important topics here. So first of all, working, I think everybody will be knowing, so we can just discuss quickly here. So what is happening? If you see, zinc will be there, it will lose electrons and come to the surface as come to the solution as Zn2+. The electrons move through here and the copper 2+ in the solutions get reduced. So here we have to remember one very important abbreviation, LOAD. Okay, what is that? Left oxidation anode negative. Okay, so that's it. That what does that mean? On the left hand side, there is the anode is present, it is negatively charged, and on anode there is always oxidation, on cathode there is always reduction. Okay, now how to represent a cell? First, suppose you have to write the anode side. Okay, that is the oxidation, then one salt bridge, and then you have to write the cathode, that is reduction. Okay, so that is how you have to write the cell notation. Next, coming to electrode potential. So we need not study this much here, but you have to know that an electrode can be positively charged or a negatively charged electrode. Okay, now what is the electrode potential? The potential difference that develops between the electrode and the electrolyte is called as electrode potential. Okay, so each so on oxidation and reduction we have, here we have an electrode and an electrolyte, here we have an electrode and an electrolyte. So the potential difference between this electrode and the electrolyte will be called as oxidation potential. Here it will be called as your reduction potential. Now if you see here, what is the use of standard hydrogen electrode is used to measure electrode potential. Okay, so this one, like whichever electrode potential you want to measure, you have to keep that on one side, and another side you have to take hydrogen electrode, and hydrogen electrode potential is assumed to be 0. Okay. Okay, now coming to cell potential, how to calculate the EMF of a cell. This is very important, formula number 1 for electrochemistry. So solutions you have to remember, 14 formulas we have done, right? Now E of the cell at standard conditions is nothing but E naught of cathode minus E naught of anode. Here you have to remember that E naught value should be in the reduction form. Okay, it should be in the reduction form. Means what? For example, copper and zinc is there, right? We got this one, Zn2 plus. Okay, and then copper 2+ to copper. So it will be given the E naught value of Zn2 plus 2Zn. Okay, this is the reduction formula. You can see 2 plus 2, reduction is happening. So the reduction potential of zinc should be given, reduction potential of copper should be given. Then we have to take E naught of cathode minus E naught of anode. Means E naught of copper minus E naught of zinc. So that is why you have to remember, this is left side is always anode and right side is always cathode. Okay, cathode minus anode. Don't do mistake in this formula. It is always cathode minus anode. Okay, now we will go to the next one. Okay, now what is this Nernst equation? We have already calculated cell EMF, right? Then what is the use of Nernst equation? So cell EMF is calculated using this formula under standard conditions. Standard conditions means the electrolyte concentration is taken as 1 molar. Now if we change the concentration of electrolyte more than like any other value, then we have to use Nernst equation. Clear? Okay, now let us see what is there in the Nernst equation. E of the cell is equal to E naught of the cell. How we will calculate E naught of the cell? Cathode minus anode minus 2 point. So this value, okay, this value will become 0.059. You have to remember 0.059 by N log of product concentration by reactant concentration. Okay, so if this is the cell reaction, then you have to take product concentration divided by reactant concentration raised to the power of stoichiometric coefficients. So this is the where you people make, definitely many of the students make mistakes here. They do not consider the coefficients. Okay, so coefficients are very, very important. That has to be taken. Do not forget it while using the Nernst equation. Okay, now what happens here? So we will calculate E naught E of the cell. So you can see under standard conditions, E naught of the cell will be higher, right? After that, under non-standard conditions, we get E of the cell. Okay, yeah. Now coming to this one. For example, this reaction, will do one small example. Okay, Zn2 plus to Cu2 plus. Now if you see the cell reaction at oxidation, it will become Zn2 plus 2 electron, right? And here at cathode, it will be copper 2 plus 2 electron gives copper. So now if I add both the reaction, 2 electron will get cancelled. So I'll get Zn plus Cu2 plus will give me Zn2 plus Cu, right? So what will be the E of the cell? E of the cell will be E naught of the cell, that is E naught of copper minus E naught of zinc minus 0.059. How many electrons are involved? 2. So 0.059 by 2 log of product concentration by reactant concentration, only ions you have to take. So Zn2 plus concentration by copper 2 plus concentration. This is not 2 power, okay? It is like this written. Zn2 plus by copper 2 plus. Okay. Now let us do this one. Let us this one. We have this one. The Ni plus, so I'll write this reaction again. Ni plus Ag plus gives Ni2 plus Ag. Okay, so now if you see what is the oxidation reaction, Ni is getting converted to Ni2 plus 2 electron. Okay, silver is getting converted from Ag plus 1 electron to Ag, right? This is undergoing oxidation, so this is anode reaction. Okay, and this is going reduction, so it is cathode reduction. Okay, now if you see here, there are 2 electrons, here it is 1 electron, so this electron will be this equation you have to multiply it with 2. Then what I will get here, 2 Ag plus 2 electrons gives 2 Ag. Now you have to add both the reaction, anode and cathode reaction. So if I add both the reaction, what I will get? So Ni is there, so I will write here Ni, okay, plus 2 Ag. Okay, so we will get Ni plus 2 Ag plus, then Ni2 plus 2 Ag. Okay, now if you see, now I want to write the E naught of the cell. So first we will calculate E naught of the cell will be equal to E naught of cathode minus anode. How to identify which is cathode, which is anode? I told you oxidation will always be anode, reduction will always be cathode. So that will be, it will be E naught of Ni2 plus, okay, sorry, E naught of Ag plus 2 Ag, because our cathode is silver, right? So E naught of Ag plus 2 Ag minus E naught of Ni2 plus 2 Ni, right? So this is the E naught of the cell. Now E of the cell will be equal to E naught of the cell, okay, minus 0.059, number of electrons is 2, log of product by reactant concentration. So you see in the product side only nickel ion is present. So Ni2 plus concentration whole divided by Ag plus concentration. Here I am telling this 2 people generally forget. Okay, this 2 stoichiometric coefficient you have to remember, right? So like this you can solve any Nernst equation question. Calculator is there. Again I am telling, it's very easy to score physical chemistry problems if you only know the formulas correctly. Okay, now coming to the next one, that is equilibrium constant and Nernst equation. So at equilibrium what happens? E of the cell becomes 0, right? Then E naught of the cell will be equal to 2.303 by RT into log Kc. So questions will be asked you to calculate for log Kc value, or Kc value is generally asked. Then if we see what is the relation between delta G and E naught of the cell. So delta G is equal to minus NF E naught of the cell. These 2 reactions are also important. So I think we have first formula, this is Nernst equation is second formula. then we have third formula and fourth formula. Okay, till now we have written fourth formulas for electrochemistry. Now coming to electrolytic cell, so here we are studying about Faraday's law and products of electrolysis. Okay, so if you see first law, according to the Faraday's first law, the mass deposited, you can just write down this much, that the amount of chemical reaction is directly proportional to the amount of electricity passed. Okay, so what is the formula? M is equal to ZIT. So if it is not visible, I'll write here M is equal to Z into I into T. Formula number 5. Now what is Z here? Z is called as electrochemical equivalent. How to calculate it? Molar mass. Okay, molar mass divided by N into 96500. What is this N? Number of electrons involved. Okay, now coming to second law. So if the two cells are connected in series, then when you are passing the same amount of current, then the mass deposited at cathode 1 by mass deposited at cathode 2 will be equal to equivalent weight of 1 by equivalent weight of 2. Okay, I'll see this formula. See, M1 by M2 is equal to E1 by E2. Now how to calculate E1? So M1 by M2 is equal to E1 by E2. E1 is nothing but molar mass of 1 by N1 into molar mass of 2 by N2. Okay, so this formula you have to calculate, and the question will be generally in this form, like they will give you one mass deposited and another mass you have to calculate. N1 and N2 are again the number of electrons lost or gained in the reaction. Okay, so that is done. So we are gone with 6th formula. This is very important, products of electrolysis, especially which one you have to remember, I'll tell. For molten NaCl, sodium at cathode and Cl2. Equations no need to remember, only the products. At cathode, sodium metal, at anode, chlorine gas. Now aqueous NaCl, if you take, hydrogen has more reduction potential, so hydrogen gas is produced and chlorine gas is produced. Now coming to dilute H2SO4, this one is generally like not asked, so but you can see at cathode hydrogen gas, at anode oxygen gas, and for concentrated H2SO4 at cathode hydrogen gas, at anode it is S2O8 2-. Now coming to next one is factors affecting electrolytic conductance. Okay, so we are now in the, so we have completed what? We completed the first types of cell we completed, galvanic cell and electrolytic cell. So in both, in galvanic cell we got some formulas, in electrolytic we got some formulas. So total we are done with now 6 formulas within the cells. Now we will go to the next topic, that is conductance. Okay, so ionic electrolytic conductance depends on what factors? Okay, electrolytic conductance means the conductivity due to the electrolyte. In electrochemistry, our conductor is electrolyte, so its conductivity depends on what factors. You can just remember, like question can be like, which of the following are the factors, which are not the factors, or like that some questions you may get. So first it depends on the nature of the electrolyte, whether it is a strong electrolyte or it is a weak electrolyte. Then the size of the ions produced and their solvation. Next, the nature of the solvent and its viscosity, concentration of the electrolyte, temperature. Okay, so these are the factors, you can just quickly point it down. Now let us see the next topic, that is conductance of electrolytic solutions. Okay, so conductance of electrolytic solution, here two important things that you have to know is kappa and lambda m. What is kappa? Kappa is specific conductance. Okay, specific conductance, and this one lambda m is molar conductance. Okay, now if you see here, what is the effect of concentration in both the conductance? Okay, so this one conductivity decreases, okay, with decrease in concentration. If you decrease the concentration, kappa value will decrease, but molar conductivity increases with decrease in concentration. First point is this one. Okay, so you can see kappa decreases with the decrease in concentration, but lambda m increases with the decrease in concentration. Now in the lambda m molar conductivity, we have two types of molar conductivity, that is due to strong electrolyte and this is due to weak electrolyte. In both the cases it will increase, but what is the condition why it increases in strong electrolyte? It is because of the increase in the mobility of the ions. And in weak electrolyte, why it increases? It is due to the increase in the dissociation of ions, right? Now, what is limiting molar conductivity? So, when you keep on diluting, the concentration becomes 0 and like almost equal to 0. That time, whatever is the conductivity, that is called as limiting molar conductivity. Okay. Okay. Now this is very important, Kohlrausch law and its application. So what does Kohlrausch law states? That the limiting molar conductivity of an electrolyte can be represented as the sum of the individual contributions of the anion and the cation. So no need to like remember the definition and all, simply you have to remember, suppose we have an electrolyte AXBY, okay, then the molar conductivity will be equal to X times of molar conductivity of A plus Y times of molar conductivity of B, right? So that is what is your Kohlrausch law. Now next we have to know is, what is the application of knowing this Kohlrausch law? Where does it help? It helps us to calculate the molar conductivity of the weak electrolyte. Kohlrausch law, students, very important. Okay, questions are asked repeatedly from Kohlrausch law. In alpha value, you can find out lambda m by lambda naught m, that is molar conductivity by limiting molar conductivity, and then we can also calculate dissociation constant using C alpha square by 1 minus alpha. Okay, so what is it? It is interrelated, right? Once we get alpha value, we can get Ka value, and for getting Ka value, you need limiting molar conductivity value, and to calculate that, we need Kohlrausch law. Okay, get it now? Okay, some products of electrolysis. Sorry, this is your commercial cells. Okay, 1 second. Okay, yeah. So these are your commercial cells. So we'll see some commercial batteries, their reactions. Okay, and it's not like all the batteries you have to remember. Certain cells, certain batteries I'll tell you which you have to, the reaction you must have to remember is, the first one is dry cell. Okay, just you should know that zinc is the anode here and MnO2 is the cathode here. Next we have mercury cell. So mercury cell also you should know zinc and mercury are the anode and cathode respectively. Then if you see lead storage, in lead storage is very important. Learn its anodic reaction and cathodic reaction completely. This is your discharging reaction. The opposite will be the recharging reaction. Then nickel cadmium, you can just remember cadmium is anode and nickel is your cathode. Fuel cell reactions also you have to remember. Okay, so what you have to remember, reactions is lead storage and fuel cell reactions, and others just you know which is anode, which is cathode. That is enough. Okay, now here some important formulas we will discuss, some more formulas here we will discuss. That is, so first of all, from Kohlrausch law we got this one. 1 second. So we have written this formula, 6th formula we got. Now let us see, next formula is your 7th one. Okay, 8th and 9th. Now coming to one more formula is there, that is kappa formula. Kappa formula, that is 10th formula, is 1 by R, okay, into L by A. Okay, so now how you are getting this one? So just if you know, we have formula is equal to R is equal to rho into L by A, right? Now 1 by rho is nothing but your kappa, so that is equal to 1 by R into L by A. Okay, so this is the formula for kappa value. What are its units? Its units are your S centimeter inverse, okay, or S meter inverse. This is the first formula, and next one you have to know is lambda m formula, that is equal to kappa into 1000 by C. Kappa into 1000 by C, where C is your concentration, kappa is again your conductivity, and 1000. So its unit is S centimeter square mole inverse. Okay, S centimeter square mole inverse. Okay, so total 11 formulas we got here. Okay, now coming to the next, third important topic, that is chemical kinetics. So again I'm telling you, we are not discussing each and everything from the chapter, only the important topics from where the questions are repeatedly asked. Those concepts we are revising in a detailed manner. Okay, so till now if you see, we have completed solutions chapter. We discussed 14 formulas. In electrochemistry we discussed how many formulas? We discussed around your 11 formulas, right? So apart from this, you have to learn the theory parts which I have told you to remember. Now going to chemical kinetics. Okay, so first of all, what are the important topics here? Rate of a chemical reaction, factors affecting rate, effect of concentration, integrated rate equation, effect of temperature, and then effect of catalyst, and then collision theory. Briefly we'll tell what is the most important. I'll take effect of temperature, integrated rate law, and effect of concentration. These three topics are very important. Okay, so now coming to first, rate of a reaction. Rate of reaction is of two types, you know, average rate and instantaneous rate. Average rate is when you calculate for a longer duration of time. Instantaneous rate is when you calculate for a particular instant. Okay, nothing too much to think. Then this is the graph for average and instantaneous rate. These graph questions are also not asked. This is important. Factors affecting the rate of the reaction: concentration, temperature, and catalyst. Concentration is there in detail, temperature is there in detail, catalyst is also explained in detail. Now first, if you see effect of concentration. So first of all, you should know how to write. From here, I'll tell you one more thing. Let us discuss here. Suppose you have a rate reaction A to the like this one reaction is there. Okay, will not put equal to, 1 second. So again, suppose you have a reaction 2A plus 3B gives 4C. Then how to write the differential rate equation, that you should know. So this is minus dA by dt. Okay, coefficient is 2, so we'll put 1 by 2 is equal to minus 1 by 3 dB by dt is equal to plus 1 by 4 dC by dt. Okay, so this is equal to what? Rate. This is how you have to write the differential equation. From here, questions are asked, numericals are asked, like they will give you the rate and they will ask you dB by dt. They will give you like A concentration and they will ask you B concentration. So you have to first write the equation, then whose two values are asked or related, those relation you have to take and then solve it. Okay, so this is our first formula, differential rate law. Now we will go to our rate law, that is any rate law means the dependency. Okay, the dependency of a rate of a reaction on concentration is given by rate law. So rate law is equal to rate is equal to K into A to the power of N, where N is the order of the reaction, K is the rate constant. Okay, now we will see about order. What is order? So what does exactly order tell? See, we know that if concentration will increase, rate will definitely will increase, right? But whether how many times the rate will increase. Suppose you are making the concentration double, then will the rate also will become double, or the rate will become 4 times, or the rate will become half time. So that depends, that is given, that information is given to us by order of the reaction. Okay, now what is the definition? It is the sum of the powers of all the concentration terms in the rate law. Okay, so now if we see, so there is something called as molecularity also. Let us see the difference. So order is the sum of the powers of the concentration terms, whereas molecularity is the total number of species reacting in an elementary step. Molecularity you can tell by seeing a reaction, but order you cannot tell by just seeing the reaction. This is experimentally determined. Okay, it depends on the mechanism. Now this can be 0, negative or positive. It is always positive. It can be a fraction or a whole number. It has to be a whole number. Okay. Next thing, this is very important, questions are asked from here. What is the general formula to calculate the unit of rate constant? Rate constant, so this is my third formula. Our second formula is this one, right, where I wrote this one. Okay, now coming to this one here, third formula. Here how questions will ask, they will give you a unit or a K constant value and you have to predict the order of the reaction. For example, it is given for a certain reaction, K value is 1.6 into 10 to the power of minus 5 mole square liter minus square second inverse. Something like this is given. Now what you have to do is, you have to equate the power of mole with the power of mole here. So n minus 1 is equal to 2. So n will be equal to 3. So this is a third order reaction, right? So that is how you can solve it. Such questions are asked. Now coming to integrated rate laws, very, very important one. So for zeroth order, what is the reaction? A naught minus A is equal to KT. Okay, A naught is the initial concentration, A is the final concentration, K is the rate constant, T is the time. Now this is my fourth formula, right? Now for first order reaction, the 2.30 KT is equal to 2.303 log A naught by A. All of you must be knowing this formula, very important formula. This is my fifth formula. Okay. So next is your graph for zeroth order and first order. You can say if you have the concentration versus time graph, right? So we have this formula, A naught minus A is equal to KT, right? So I have concentration at any point of time, is that is A versus time graph. So we will get this equation, I will write like this. This one I'll take this side and I'll write KT plus A naught, right? So you can see I can write it in the form of y is equal to mx plus c. So slope is negative with A naught as an intercept. Similarly, you can draw for first order reaction. Okay. Now graph is not that important, but you should know some basics how to derive the graph. If question is asked, you can solve it. Now this table is very, very important. You have to remember for the zeroth order reaction, differential rate law is minus dr by dt minus k. This is not here, half-life formula is there, r naught by 2k, and here 0.693 by k for first order. And then you have the integrated rate law, and you have the integrated rate law here, and the units of k is also given, right? So these are very, very important thing. Now coming to next one, that is effect of temperature. Very simple and easy concept. K is equal to A into e to the power of minus Ea by RT. That is your Arrhenius equation. Here you have to remember, if activation energy will decrease, rate constant will increase. Okay, this point you have to remember. Next is what is here, what are the values? A is Arrhenius factor, R is rate constant, then K is rate constant, E is activation energy, R is gas constant, and T is temperature. Now, if we have two different temperatures, when we increase the temperature, the rate constant increases, right? So, when we have two different temperatures, T1 and T2, so at T1, the rate constant is K1, at T2, the rate constant is K2, then what is the activation energy, how to calculate? So, that is the formula here, log K2 by K1 is equal to EA by 2.303 R whole T2 minus T1 by T2 into T1, right? So, here T2 and T1 are the temperatures and K1, K2 are the respective rate constant. EA is the activation energy, right? So, this formula is also very used. This one is also used. You can get, okay. Now, what is the effect of temperature? That is what we are continuing. So, what happens when we increase the temperature? You can get a theory-based questions from this graph. So, according to this one, what happens when you increase the temperature? The number of molecules which can react. Okay, so molecules cannot react directly. They need to possess some energy. So, the number of molecules having that required energy will increase. As the number of molecules having the required energy increases, then more molecules can react, and that is when rate will increase. Okay, and then this is the graph for your Arrhenius equation. So we have just take ln on both sides, and then ln k versus 1 by t will get a negative slope. Okay, so okay, now coming to this one, effect of catalyst. This is also very important. When catalyst you use, it provides an alternative pathway and reduces the activation energy. So if you can see here in the graph, first the reaction activation energy was this much, and then the activation energy decreased. And just now I told you, if activation energy decreases, right, if activation energy will decrease, rate constant will increase, rate will increase. So that is why rate increases. So what is the role of catalyst? It provides an alternative pathway for the reaction which has a lower activation energy. Okay. Now, just coming to collision theory, not like nothing much to remember. You have to just understand a few things. That first of all, the molecules are assumed to be hard spheres, and the reactions are assumed to occur only when these spheres collide with each other. Okay. Next, according to collision theory, this was the equation for rate, which is now replaced with your Arrhenius factor. Okay. Now, what is activation energy? So you can also know what is collision frequency. Collision frequency is the number of collisions happening per second. Okay, so these definitions are not asked in the exam, nothing much to worry. Now this is important. Activation energy, I told you, is the minimum energy or the extra energy that is required for the reacting molecule to get converted into product. So if you see here, this was the reactant energy. See, this is the energy of the reactant, right? And after getting this energy, the reactant will start forming products. So this is called as your threshold energy. So from the reactant energy to reach to threshold energy, the energy that is required to keep or to make the reactants reach the threshold energy is called as your activation energy. Okay, so that is there. Okay. So then here you have to see for exothermic reactions, EA forward reaction is less than the EF backward reaction. Can you just imagine this one? So if we have exothermic reactions, okay, so I can draw the graph of exothermic reactions here. So exothermic reactions means product's energy will be lesser than the reactant energy. So if you see here, what is the activation energy for the activation energy for the forward reaction is this one. The activation energy for backward reaction is this one. So which is greater? EA forward will be lesser than EA backward. Now, if we have endothermic reaction, okay, so if you do endothermic reaction, the reaction is like this. Product energy will be more. Then if I find the activation energy, this is the activation energy for forward reaction, this is the activation energy for backward reaction. So EA forward is greater than EA backward. Okay, so questions can be asked from here also. Calculation based questions are asked. So just revise this topic. Okay, so this were the most important topics from chemical kinetics. Nothing much formula is there. Half-life formula, integrated rate law formulas, and then differential rate equation and rate law. Okay, so such type of easy questions, easy calculations questions are asked. So just revise this topic once and then go to our top 30 questions from chemical kinetics. Just solve them once. You will be very easily, you can complete this physical chemistry kinetics chapter. Okay, so now let us go to the next chapter, that is thermodynamics, which is very vast topic. But the good news is in the exam you do not get questions from all these topics. Very specific topics are there from which you can expect questions, and repeatedly from last 7 years the questions are asked from the same topic only. So we can, if we do that topic particularly, so we can revise it and we can do it in the exam. So don't leave this topic. Whatever I'll tell now, which you have to focus, so just focus on that thing and then go for the exam. Okay, so quick 5 to you can take hardly 15 to 20 minutes to complete this chapter if you focus only from where the questions are asked. So what are the important topics here? First one is your basic terminologies, second is work, third is internal energy, fourth is first law of thermodynamics, fifth is relation between delta H and delta U, then heat capacity, and then we have second law of thermodynamics, and then Gibbs free energy. So which is the thing that you have to most focus? Formula for work, internal energy, delta H and delta U, delta G. Okay, these 4 things you have to focus more. Okay, now let us quickly see. Here are the basic terminologies for the thermodynamics chapter. So first is, what is a system? System is the part of universe which you are considering. Open system is there can be exchange of both energy and matter. Closed system, there can be energy of only, no mass but only energy. And isolated system, there is no exchange of matter or mass, right? Neither exchange energy nor matter. Okay, now coming to surrounding. So anything except your system is called as surrounding. Boundary, the thing that separates your system and surrounding. State variables and state functions. So state variables tells about the state of a system, and state functions we have which does not depend on the initial, these are which does not depend on the path and only depend on the initial and the final state. So here you write down these examples, you have to remember. Questions are asked, which of the following is not a state function, which of the following is a state function, right? So that's why you have to remember all these examples: pressure, volume, temperature, internal energy, enthalpy, and entropy, right? Okay, let us go to the next part. Here also this, whichever I'm putting star mark, if you have not completed thermodynamics at all, these star mark things you have to do and go. Okay, so intensive properties and extensive properties. So examples here also you have to remember: temperature, pressure, density, concentration. Intensive properties are those which do not depend on the amount of substance. Extensive properties are those which depend on the amount of substance, right? So you can see volume, energy, enthalpy, entropy. Okay, now coming to here, these 3 are also important. Types of processes: isothermal, isobaric, isochoric, adiabatic. So what is constant in which pressure you should know? In isothermal, temperature constant, isobaric pressure constant, isochoric constant volume, adiabatic no heat of constant heat or no transfer of heat. Now coming to cyclic process, reversible, irreversible. So cyclic process is when initial and the final state is same, that is called cyclic process. Reversible, the process which takes in infinitely small steps, we call it reversible. And irreversible are those which occurs in a fast and cannot be come back or cannot be reversed. Okay, okay, so here it is important, all the natural processes are of irreversible nature. Okay, fine. Now we will go to our first formula, that is work done. Okay, work done, the general formula is minus P external V2 minus V1. Okay, now what happens? If the process is isothermal and reversible, then work done formula is equal to minus 2.303 nRT log of V2 by V1. First formula, second formula, very important. Okay, this formula is very important. Here we can also write this like minus 2.303 nRT, okay, log of P1 by P2. Okay, so this is the formula from where majority of the questions are asked. You have to just know the R value. Also I'll tell you what will be the R value here, 8.314. Okay, units of work done will be joule. Clear? So now if pressure, this formula either you can use or this formula you can use based on the question. If isothermal reversible is mentioned, then this formula. If nothing is mentioned, then that formula. Clear? Okay. Now let us go to the internal energy. So what is internal energy? It is the sum of all the possible types of energy present in the system. Like we have rotational, kinetic, attraction, and then vibrational. So all the sum of all the energies is called as internal energy. Then what is another definition of delta U? So it is heat change for a reaction taking place at constant temperature and volume. This is very, very important. Okay. So delta U is the heat exchange at constant volume. Next you have, so this is delta U. What is it? It is a state function and it is a extensive property. So you should know these two things, that it is a state function and it is an extensive property. Next, the value of delta U is negative for exothermic reactions and where it is positive for endothermic reactions. Clear? So if you give endothermic, means you will provide heat, internal energy will increase. So that is why delta U is positive. If you remove heat, energy will decrease. So delta U will be negative. Okay. Okay. Next, going to this one. First law of thermodynamics here also. So this is my third formula. Very, very important. Here you have to understand sign convention also carefully. So delta U is equal to Q plus W. Now here are three conditions. If the process is isothermal, okay, delta U will become 0. Then what is remaining? Q will be equal to minus W. Okay. Q is what here? Q is heat. Okay. And W is work done. I hope this one will be knowing. Okay. Now if you see, if process is adiabatic, Q is 0. Then delta U will be equal to W. Next, isochoric. In isochoric, work done will be 0. W will be 0. Then delta U will be equal to Q. Right? Once again, let us revise this one. Isothermal, delta U 0. That means Q equal to minus W. Adiabatic, Q is equal to 0. Then delta U is equal to W. Then we have isochoric. Volume is 0. Like delta V is equal to 0. So work done is 0. Delta U is equal to Q. Okay. Now apart from this, here you should know about sign convention. So listen carefully. If work is done by the system, okay, work is done by the system, then it is negative. If work is done on the system, okay, then it is positive. Clear? This one. Now next is about Q. If Q is supplied, okay, the system gains heat, then Q will be positive. And if system loses heat, Q is lost, okay, then it will be negative. Clear? Okay, so this is this first law of thermodynamics. Next we have enthalpy and internal energy relation. These formulas are also important. So we had formula number 4 and formula number 5. Delta H is equal to delta U P delta V, where delta H is your enthalpy. Okay, now this is your enthalpy. Okay. Now what are the properties of this one? Enthalpy is also extensive property and is also a state function. Okay. And delta H is also equal to 0 for isothermal process. Okay. Now delta H is equal to delta U plus delta Ng RT. This reaction, instead of P delta V, we can write it as delta Ng RT. Now how to write, how this formula has come? Like for example, you have a reaction N2 plus 3H2 gives 2NH3. Okay. Now if how to calculate delta Ng? Delta Ng will be the number of moles of products, gaseous products, minus the number of moles of the reactants. So if you see here, we have 2 moles on the product side, minus 3 plus 1, that is equal to 4. So we will get minus 2. Delta Ng value will be minus 2. Clear? Now, so that is how you can use this formula to calculate the enthalpy of any reaction. Okay. Now let us go to the next one. So heat capacity, not much questions are asked. So just you can note that basic formula. Heat capacity is the amount of heat to raise the temperature of a substance by 1 degree, dQ by dt. Specific heat capacity is to raise the temperature of 1 gram of a substance by 1 degree. So it is heat capacity by mass in grams. Okay. Next, if you see molar heat capacity is the heat required to raise the temperature of 1 mole of a substance by 1 degree, 1 mole. So that is heat capacity by molar mass. Okay. Next, this is very, very important. Okay, what is the heat capacity at constant volume is called as CV. Okay, and the formula for that is du by dt at constant volume, and Cp is dh by dt at constant volume, sorry, at constant pressure. Okay, clear? These two are very important. Then what is the relation between Cp? This is the well known formula, Cp minus Cv is equal to R. Okay, fine. Then coming to second law of thermodynamics, here also nothing much you have to remember. You have to just know that delta S is equal to Q by T. Okay, not a very important formula. So I will write fifth, right? So we have sixth, seventh and eighth. These two formulas you might skip. That's questions are not asked from much from these questions. Then this one is your ninth formula. Okay. Next, entropy. What is entropy? Entropy is the degree of randomness. How much entropy is there? So here questions are asked, like options are given in which entropy is positive, entropy is negative. So you have to remember, if the phase is changing, okay, phase is changing, then entropy will increase. So like solid to liquid, liquid to gas. If, like for example, reactants were solid and then products are liquid, then entropy increases. Reactant is liquid, product is gas, then also entropy is increasing. Okay. Next, in that case, entropy will increase. Another case, if gaseous products are formed. Okay. Suppose the reactants are completely solid, and like in the reactant there are two gas molecules, and in the product side the number of gaseous molecules produced is more. So in that case also the entropy will increase. Another case is if number of particles increased. Number of particles increased. Like for example, in a reaction it became A2 to 2A. Here you can say there is only 1 mole, but here there is 2 moles. Number of particles has increased, so entropy will also increase. So such type of questions are also asked. Now the next very important formula is Gibbs free energy. From here many questions are asked, many questions are asked. Delta G is equal to delta H minus T delta S, this formula. Okay, and we have one more formula, that is delta G is equal to minus 2.303 nRT log K. Here, from here the conditions for what is the condition for spontaneous reaction? For that delta G should be negative. Okay, so from this condition also many questions are asked, like when delta H is positive, delta S is positive, then what should be the condition, what should be the value of T? And one more thing that you have to remember is delta G is equal to 0 at equilibrium. Okay, so these were the important concepts. Okay, now one more thing from where questions are asked repeatedly is from your Hess's law. Okay, Hess's law has no formula, but you have to practice some certain questions, like 3-4 reactions are given and you need to know one required reaction. So you have to arrange and rearrange the given equations to derive the required reaction. Then in that case, whatever enthalpies operations you are doing, that will be used for Hess's law. So in our top 30 questions from thermodynamics, many questions we have solved from Hess's law. So please do watch it. It's very easy to solve. Only you have to just know the equation and then you have to start solving it. Okay, so these are the basic important formulas from thermodynamics. Again, if I tell what you have to focus majorly is your first formula, that is work done formula. Next you have to focus on your first law of thermodynamics, that formula, and then you have to focus on delta G is equal to delta H minus T delta S. So these three formulas are the major formulas from this chapter. Okay, now let us go to the next topic, that is equilibrium. Okay, so in equilibrium we have two types of equilibrium, chemical equilibrium and ionic equilibrium. So we will first see the topics under equilibrium. First is expression for Kc and Kp, how to write. Second, we have the relation between Kp and Kc. Third, Kc and the stoichiometric coefficient. So this is also important topic. Next you have reaction quiescent and its application. Next we have Le-Chatelier principle, then acid. So from here ionic equilibrium will start, acid base theory, pH of weak acid, pH of buffer, pH of salt hydrolysis, and then solubility product. Okay, so let us start with this. So first is your expression for Kc and Kp. For any reaction A, B, B gives C, C, D, D, the Kc value will be the product's concentration raised to the power of their coefficient divided by the reactant concentration raised to the power of their stoichiometric coefficient. Now, if we write that in the terms of pressure, then it will be Pc, Pd, Pa, Pv. Okay, very easy. Now, what is the relation between Kp and Kc? So, Kp is equal to Kc into RT to the power of delta Ng. Okay. Now, same thing how we calculated delta Ng, that is number of moles of gaseous products minus number of moles of gaseous reactants. Okay. Now here three conditions arises. If delta Ng is equal to 0, then Kp will be equal to Kc, right? You can see this term, if it is 0, then RT to the power of 0 will become 1, then Kp will become equal to Kc. Now if delta Ng is negative, right, then what I can write? Kp will be equal to, suppose it is minus 1, Kc by RT, right? So in that case, what I can say? Kc will be greater than Kp. Okay. Now if delta Ng is positive, then what equation will get? Kp is equal to Kc into RT. In that case, Kp will be greater than Kc. So such three conditions arises. Okay. Now we'll see the extent. This is also very important, Kc and the stoichiometric coefficients. So there are three operations in Kc that you should remember. Like for example, you have a reaction A is equilibrium with B to the power of B, and the equilibrium constant for this one is K1. Now what you have done, you have multiplied N to the whole equation. So what I'll get? NAA gives NBB. Now when this N is multiplied to the whole equation, what will be the new K? The new K will be K1 to the power of N. Okay. This is the first thing that I want to tell. Now if I want to reverse this reaction, suppose I want to write like this. BB gives AA. So when a reaction is reversed, the equilibrium constant becomes inverse. So now the new K for this one will be 1 by K1. Clear? Now the third one is if two reactions are added. Like for example, AA gives you BB, the equilibrium constant is K1, and then we have BB gives CC and the equilibrium constant is K2. Now if you add both these reactions, what I'll get? AA gives CC. So when two reactions are added, the equilibrium constants are multiplied. So K will be equal to K1 into K2. Clear? Okay. From here questions are asked. They will give you like two equations and you have to find the K value. So you have to remember what is done. Like the relation between the two reactions, if you can derive, then you can easily solve this question. Okay. Now let us go to the next one, reaction quiescent. So what is the difference between equilibrium constant and reaction quiescent? Equilibrium constant is that when you take the concentrations, the reaction has already reached the equilibrium, and the concentrations are the equilibrium concentrations of the reactants and products. But reaction quiescent is the concentration at any point time t. Okay, at any time you have taken the concentrations and you have measured the ratio, then how you can tell whether the reaction will go in forward, backward, or at equilibrium? So we have a condition for that. If the reaction quiescent is greater than K, then the reaction will go in backward direction. If Q is less than K, then the reaction will go in forward direction. And if Q is equal to Kc, then the reaction is already at equilibrium. Okay. Now let us see the Le-Chatelier principle. Again, a very important topic. Definition is not required to remember. Just you have to understand that if you are disturbing the equilibrium, okay, you are disturbing the equilibrium. What are the ways in which you can disturb the equilibrium? You can change the concentration, you can change the volume, you can change the temperature, and then you can change the pressure, and you can add any inert gas. Okay. So now if you change the equilibrium, or if you want to disturb the equilibrium has like forward direction and backward direction. It will adjust itself. Okay. It will either go more in the forward or less in the backward. It will adjust itself so that the change that you have introduced will be neutralized or will be cancelled. Okay. Now, so now for that you have to remember, if you are increasing the temperature and the reaction is endothermic, okay, endothermic reaction is there and you are increasing the temperature, then the reaction will go in forward direction. If it is exothermic and you are decreasing the temperature, then it will go in forward direction. Clear? Endothermic reaction, increasing temperature, forward direction. Exothermic reaction, decreasing temperature, forward direction. And that means what? The other things will be opposite. Like if you decrease the temperature, it will go backward. If you increase the temperature, it will go backward. Clear? Second one is effect of concentration. So concentration, if you see reactant concentration, if it is increased, then reaction will go in forward direction. Product concentration, if it is increased, reaction will go in backward direction. Then third one is effect of pressure. So here if you increase the pressure, then the reaction will try to decrease the pressure, and we know pressure is directly proportional to number of moles. So whichever side is less number of moles, reaction will shift to that direction. Okay, so what is there? If increase in pressure is there, towards less number of moles. So here there is no forward and backward. You have to just count the total number of moles, gaseous moles. So whichever side there is less number of gaseous moles, that side it will go. Next is effect of volume. So if you increase the volume, it will go towards more number of moles, just opposite of each other. Okay. Next, effect of catalyst. There is, like, if you add catalyst, there is no effect. Now, if you add inert gas at constant pressure, then it will go towards more number of moles, and at constant temperature, it has towards less number. Sorry. At constant temperature, it has no effect. Okay. This is actually at constant volume. Please change this one. At constant volume, there is no effect. At constant pressure, towards more number of moles. Clear? So all the factors are clear. Just revise it, learn it properly, and then go for the exam. Okay, now coming to your ionic equilibrium, we'll start. So here we have first of all 3 definitions of acids and base. Arrhenius definition is one which can donate H plus, bases give you OH minus. According to Bronsted, acid is a proton donor, base is a proton acceptor. Now here we have conjugate acid base questions are asked. Okay. So what is conjugate acid and base pair? So they differ by 1 H plus. Differ by H plus. Okay. So now if you want to find the conjugate acid, okay, conjugate acid of any X, then you have to add 1 proton. Okay. And if you want to find conjugate base of anything, okay, conjugate base of, for example, anything, then that molecule must behave as an acid, so you have to remove 1 H plus. Clear? So this thing you have to remember, and here from here questions can be asked. Then we have Lewis definition, acid is electron acceptor and base is electron donor. And then strong and weak electrolytes, strong acids are like complete dissociation, weak acids are weak dissociation or partial dissociation. You can see examples HCl and CH3COH. Okay. Now this is very, very important slide where you have most of the important formulas. First is your pH of a weak acid. So weak acid means they will not dissociate completely, they will dissociate partially. So there is something called as a dissociation constant for a weak acid. How to calculate the dissociation constant? Ka is equal to C alpha square minus 1 minus alpha. So what is this alpha? Alpha is the degree of dissociation. How much it is dissociating? Like it will not dissociate 100%, that is clear. But whether it is 60%, 50%, 40%, 5%, right? So that is your degree of dissociation. C alpha square by, one second, this formula is, I'll change this one. Alpha is equal to root over of Ka by C. Okay, this one please change it. Alpha is equal to root over of Ka by C. Now coming to ionic product of water, concentration of H plus into OH minus is 10 to the power of 14 at normal conditions. Then pH plus POH is equal to 14. Now what is the H plus concentration if it is a weak acid? H plus concentration is C alpha, and we know we can write like this, C into alpha value I can write like this, root over of Ka into C. Now this C we can cancel and I'll get root over of Ka into C. Okay. Okay. So we will get root over of Ka into C for the H plus concentration. Okay. So once again we can discuss this one. H plus concentration for a weak acid is C into alpha. And if you see C into alpha value, I'll put this one root over of Ka into C. So I'll get root over of Ka into C. Okay. So now if you see for the pH value, pH will be equal to half of pKa plus log C. Okay. Sorry, half of pKa minus log C. So now how this formula is coming? See, that is my A value. Like I can say now, H plus concentration is equal to root over of Ka into C. Okay. Now what we have to do? We have to calculate the pH value. pH is negative logarithm of H plus. So I can write pH is equal to minus half log of Ka into C. So this minus will be multiplied inside. So minus, I'll take half outside, minus of log Ka and minus of log C. Minus log K is nothing but pKa minus log C. Okay. So you need not derive this formula, you can just know the values half of pKa minus log C. Clear? Now coming to buffer solutions. So buffer solutions are those which can resist the change in pH, right? Buffer are of two types, acidic buffer and basic buffer. Acidic buffer is made up of weak acid and its salt with strong base. For example, we have a weak base CH3COH, weak acid, and a strong base. So what will be the salt of this one? We will get CH3COONA, right? So these two mixture, weak acid and its salt with a strong base, will give you the acidic buffer. What is the formula? pH is equal to pKa. Whose pKa? The weak acid pKa plus log of salt concentration by acid concentration. Now similarly, we can calculate basic buffer, weak base and the salt with a strong acid. For example, you have a weak base like NH4OH, okay, and the strong acid is suppose HCl. Then we will get salt as NH4Cl, right? So this combination, weak base and a strong salt and a salt with a strong acid, will form a basic buffer. So POH will be equal to pKb plus log of salt by base. Okay. Okay, now coming to salt hydrolysis. So there are three types of salt which undergo salt hydrolysis, that is salt of a weak acid and a strong base. You can see the example. For that, what is the formula? CH3CONA is a weak acid, NaOH is a strong base, so the salt will be a salt of weak acid and strong base. So pH formula here will be 7 plus half pKa plus log C. Okay. Now strong salt of weak base and strong acid, so NH4 and Cl, right? So here the pH will be 7 minus half pKb plus log C. Now a salt of weak acid and weak base is your CH3CO and NH4. Okay. So now ammonium acetate. So 7 minus half pKb plus half pKa. Okay. So these values will be given, just you have to remember the formulas. Okay. Next is your solubility product for any salt of type AXBY. Okay. What is the solubility product? That the solubility, so X to the power of X, Y to the power of Y, S to the power of X plus Y. For example, we have salt of barium chloride. This is X is equal to 1, Y is equal to 2. So 1 to the power of 1, 2 to the power of 2, S to the power of 2 plus 1, that is 3. So we can write 4S cube. Clear? Okay. So I think, yeah. So these were the important topics from chemical equilibrium and ionic equilibrium. If you find ionic equilibrium difficult, you can leave that for now. Chemical equilibrium, Kp-Kc relation, and then how to write the expression of Kp and Kc. That things you can remember, and the stoichiometric coefficients, how it is related, this you can easily solve. Again, if you want to practice some 5-10 questions, you can watch our top 30 questions from equilibrium chapter, and then you can practice those questions for the exam. If you have any other book also, you can use it as a reference. Okay, now coming to the next chapter, very easy chapter, that is your structure of atom. Few formulas from here, if you revise, you can easily get the questions from here. So first is, let us see the topics in this chapter. We have atomic terms. We will just discuss what is atomic number, mass number, isobars, isotopes, and all. Then we have electromagnetic waves, atomic spectra of hydrogen. This is important. Then photoelectric effect, Bohr's model, de Broglie hypothesis, and Heisenberg uncertainty principle, quantum numbers and rules for filling of electrons. Okay. Yeah. So we will discuss again, if I tell which are the most important, this one, electromagnetic waves, Bohr's model, de Broglie hypothesis, and Heisenberg quantum numbers. Yeah, you can say like 1, 2, 3, 4, 5 topics out of 8 are very important. Like questions are picked from these topics. Okay. Now quickly let us revise the atomic terms. Atomic number Z is the number of protons. Mass number is the number of protons plus number of neutrons. Okay. Then nucleons is present inside the nucleus, that is protons and neutrons. Isotopes are same atomic number, different mass number. Isobars, the opposite, same mass number, different atomic numbers. Isotones are that those who have same number of neutrons but different number of protons or mass numbers. Then you have isoelectronic species. These are the species having the same number of electrons. So quickly you can revise it, very easy definitions. Next, coming to wave, this is important. What is these definitions are not important, but the formulas are important. Wavelength is what? Distance between two neighboring crust or two neighboring trough. So if you have seen, we have a wave like this, right? If I draw, so between two neighboring, the distance between two neighboring crust or two neighboring trough. So this is called as your wavelength. Then frequency is the number of cycles that has been completed in 1 second. Here this formula you have to remember, C is equal to lambda into mu. Wavelength, frequency, speed of light. Okay. Now wave number is number of wavelengths per centimeter. Velocity is the distance traveled by the wave per second. Amplitude is the height of the crest or the top. Okay. Now coming to this one, hydrogen spectra. This is very, very important. In hydrogen spectra, like what does it tell? When electron goes from one level to another level, it emits radiation, right? For example, we have different energy levels for hydrogen. When an electron jumps from one level to another level and then when it comes back, it emits the radiation. We have to calculate the wavelength or the energy of this emitted radiation. Okay, so the formula for that is equal to 1. So in this formula, we are calculating the wave number. Okay, wave number of the emitted radiation. Clear? When electron jumps from one level to higher level and then when it comes back to the lower level, it emits radiation. We want to calculate the wave number of this emitted radiation. The formula for that is RH into 1 by N1 square minus 1 by N2 square. So N1 you have to remember is the lower value and N2 is the higher value. It means suppose an electron jumps from 5 to 2, right? So N1 will be your 2, N2 will be your 5. Clear? Now in this RH value is 109,677 centimeter inverse. Okay. Now based on the destination, like from wherever it starts but where it reaches, based on that we have a different spectra of hydrogen. So if the N1, see here, if the reaching point means from wherever it excited level, it ends at N1 is equal to 1. Okay, it ends at the first orbit, then we call it as Lyman series. And this energy or this emitted radiations from any level to N1 level lies in the UV region. Now if it ends at like second N2, whatever radiation stops at second energy level, we call it Balmer series, and this one comes in the visible region. If all the radiation end at third region, third energy level, then we will call it as Paschen series, and this falls in the IR region. Similarly, if the energy of the electrons stop at fourth energy level, we call it bracket, and this also forms in the IR region. And if the electron stopped at the fifth orbit or fifth energy level, we call it P fund, and it is also IR radiations. Clear? Okay, next we will go to photoelectric effect. Very simple thing. Let us quickly revise. So when the ejections of electrons takes place from the surface of the metal when light of suitable frequency falls on it. So any metal is there, you put light of suitable frequency, electrons will be ejected out. Then the minimum frequency required for the ejection of electrons is called as threshold energy. So any energy will not do, any minimum frequency is required. That minimum frequency is called as your threshold frequency. The energy of ejected electrons is directly proportional to the frequency of the radiation. Next, number of electrons ejected per second depends on the intensity of the radiation. Now, what is this one? H nu is equal to H nu 0 plus half mv square. So, this is the energy of radiation, okay, which you are putting on the metal. Now, this is the minimum energy required, or we can say threshold energy. Okay. So, now suppose, now this one is the kinetic energy of the electron. Okay. So, just you can understand, to remove an electron, you need suppose 5 joules of energy. You have given 12 joules of energy. So, 5 joule out of that 12 joules of energy that was given by the radiation, 5 joule was used for to remove the electron from the nucleus. Then the rest 7 joules will be used as the kinetic energy of the electron. Okay. So, that is the formula. H nu is equal to H nu 0 plus half mv square. Here nu 0 is called as your threshold frequency, H nu 0 is called as the threshold energy. Okay. Okay. Next we'll go Bohr's model. So Bohr's model is very simple. Electrons revolve around the fixed orbits. You don't have to remember these all things, but you have to know. And then the angular momentum is an integral multiple of h by 2 pi. Then when electrons absorb energy, they go to the higher level, and when they release energy, they come to the lower level. Then energy absorbed or released depends on the delta E, that is E2 minus E1 equal to h nu. Now here some important formulas you have to know. the energy of any orbit is minus RH by 1 by n square. For a hydrogen-like species, what do you mean by hydrogen-like species? The number of electrons will be same. And the radius of nth orbit is given by 52.9 dot n square by z picometer. Energy of nth orbit minus 2.18 into 10 to the power of minus 18 z square by n square unit is joule. Minus 13.6 z square by n square unit is EV. 313.6 z square by n square calorie per mole. These two units you have to remember. Now velocity of any orbit 2.18 into 10 to the power of 8 z by n. So where n is equal to 1, 2 and 3. Okay. So you have to remember which formulas from here. This one and this one and this one. Okay. Very simple one. Next, let us quickly finish de Broglie hypothesis. According to this, what happens? Even the matter can behave as a wave. So if they are behaving as a wave, they will have a wavelength. So the formula to calculate the wavelength of the matter wave is your lambda is equal to h by mb or h by p, where m is the mass, v is the velocity, h is the Planck constant, 6.63 into 10 to the power of minus 34 joule seconds. Okay, and p is the momentum. Right, so I'll write here mass and velocity. Now, what is Heisenberg uncertainty principle? According to this principle, the position and momentum cannot be determined simultaneously. Delta x is the uncertainty in position, delta p is the uncertainty in momentum. This is greater than or equal to h by 4 pi m, where h is the Planck's constant, okay, and 4 pi m is the mass. Okay, so we cannot calculate the position and momentum accurately simultaneously. Okay, if you calculate position correctly, momentum there will be some error. If you calculate momentum correctly, position will have some error. Okay. Okay. Now we will discuss the next thing, that is quantum numbers. Very easy thing and important also. Principal quantum number, the value starts from n to 1 to 2, 3. What information it gives you? It tells you about the energy of the shell. Next is your azimuthal quantum number. Its value starts from L is equal to 0 to L is equal to n minus 1. And what does it tells you? It tells you about the subshells. Or we can say it tells you about the shape of the orbitals. Next one is your magnetic quantum number. Its value lies from minus L to plus L. What does this information tells us? This information tells about the orbitals, or we can say their orientation. Spatial orientation, how, in which direction, x direction, y direction, z direction, which direction the orbital lies. Then spin quantum number tells about the spin of the electron. Its value is plus and minus half. Let us take an example for this one. Suppose n is equal to 3. Okay, so n is equal to 3. Then what are the possible L values? That is your azimuthal quantum number. If you see, what are the range of L value? 0 to n minus 1. N is 3 here, n minus 1 means 3 minus 1, 2. So the possible L values are 0, 1 and 2. Okay. Then what are the possible ML values? So if you know, for 0 S is used, for 1 P is used, and for 2 D is. Okay. Sorry. 1 second. Yes. SPD. Okay. So now if you see, we have 3. So what is this orbit, this subshell name? 3S. This is 3P and this is 3D. Now, if you want to calculate ML values is from minus L to plus L. So, minus 0 to plus 0, there will be like it is 0 only. So, here only 1 ML value will be there. So, 3S will have only 1 orbit. Now, if you see ML for 1, so this is minus 1, 0 and plus 1. Right. So, minus 1, 0, plus 1 as having 3 values. So, we tell it as 3P has 3 orbitals. Next, if you see 3D, minus 2, minus 1, 0, plus 1 and plus 2. So, there are 5 orbitals here, right? So, here if you see, these are 3D orbitals. Then in this 3D subshell, there are 5 orbitals, right? So, that is how you can do. Next is node. What is node? Node is the position or the place where the probability of finding of electrons is 0. So, there are 2 types of node, radial nodes and angular nodes. Radial nodes formula is n minus L minus 1. Angular nodes is formula is L. Total number of formula is n minus 1. For example, given 3D. Okay. In 3D orbital, how many nodes are there? So, if you come to calculate, what is the n value? 3. What is d value? 2. Now, the total nodes if I want to calculate, that will be 3 minus 1, 2. Now, if I want to calculate radial nodes, that is n, that is 3, minus L minus 1. So again this is 0. Then if I want to calculate angular nodes, that is L, which is equal to 2, right? So we can calculate in this way. Okay. Okay. Now we can just see some rules that has been the statements you can know while filling the electrons that you have to keep in mind. So first is our Aufbau principle. What it tells us that electrons should be filled in the increasing order of the energy levels. So electrons are added one by one to the various orbitals in order of their increasing energy. The one which is having least energy will be filled first, then the one which is having more energy will be filled at last. Correct? Okay. Next, in neutral isolated atom, the lower the value of n plus L, the lower is the energy. So how you will know which orbital is having how much energy? We have to follow n plus L rule. Now for example, if you have 3s and 2p, what is the n value here? 3, L value is 0. Okay. Then here n plus L, 2 plus p value is 2. Sorry, p value is 1. 1 second. Yeah, p value is 1. So that is also 3. So if when both n plus L value comes together or comes the same, then we have to consider whose n value is less, its energy is less. Like for example, here n value is less 2. So 2s value will be, 2p value will be less than 3s. So in that way we can calculate and we can tell the order. So first 1s, then 2s, then 2p, 3s, 3p, 4s and 3d. This one you can check. 4s value is 4 plus 0, 4, 3d, 3 plus 2, that is 5. Right? So this value is coming higher. So that is why its energy is higher and first 4s will be filled, then 3d will be filled. Similarly 4p, 5s, 4d, 5p, 6s, 4f, 5d. This rule you should know. Now next is Pauli's exclusion principle. What does this tell? An orbital contain a maximum number of 2 electrons and these 2 electrons must have the opposite spin. So whenever you fill the electrons in an orbital, you must represent in this way. They are in the opposite spin. Okay. Next, Hund's rule of maximum multiplicity. So this tells us electron pairing in p, d and f orbitals cannot occur until each orbital of a given subshell contains 1 electron each or is singly occupied. Now for example, you want to fill p5. Okay. So what you have to do is, in p there are 3 orbitals, 1, 2, 3, 4, 5. You cannot fill in this way. This is the wrong way of filling. What you have to do is, you have to first fill one. Okay, let me take the example of P3 first. Okay, if P3 is there, you cannot fill it like this. This is incorrect because one orbital is still empty. So first you have to give 1 electron to all the orbitals and then pairing of electrons will start. So what should be the correct way of filling it? We can fill it in this way. We can fill it in P1, then here 3 electrons first you have to give to each orbital. Now P4 is there, then it will start pairing. Clear? Okay, so yeah, so these were the important concepts, important topics to revise from your structure of atom. So once again, if I revise, I'll recollect, like you have to revise the Bohr's formula, okay, then you have to revise the Heisenberg uncertainty principle, then you have to revise de Broglie hypothesis. Photoelectric effect questions are less, so just you can draw the formula. Then you should know this formula that hydrogen atomic spectra questions are a must, so prepare atomic hydrogen spectra properly. Clear? Okay, so now we will go to the last topic and like very easy topic, some basic concepts of chemistry. This topic is like the backbone of the whole physical chemistry. You should know important formulas from this chapter definitely. So now let us see. First one, what are the chapters in or the topics in this chapter? Laws of chemical combination. Second is mole concept. Third is percentage composition, molecular formula and empirical formula, limiting reagent, and then you have concentration terms. Okay, now let us see these topics in detail. First is your laws of chemical combination. So we have 5 laws. First is your law of conservation of mass. According to this, mass can neither be created nor be formed. Law of constant proportion, it tells that a chemical compound always contains same elements in definite proportion by mass. It does not depend on the source of the compound. Like for example, if you have taken water molecule, what is the mass ratio? You have hydrogen is 2 and oxygen is 16. So 1:8, right? So whenever you take water from any source, the mass ratio of hydrogen and oxygen will always remain constant. Next, law of multiple proportion. When 2 elements combine to form 2 or more than 2 different compounds, then the different masses of one element B, which combine with the fixed mass of other element, bear a simple ratio to another. So like for example, we'll take the example CO and CO2, right? What is the mass of carbon? 12, oxygen mass is 16. Here carbon mass is 12, oxygen mass is 32. So here which mass is fixed? Carbon mass is fixed. So if you take the ratio of oxygen from both, it will get a simple number ratio. So what is the mass of oxygen in CO? 16. What is the mass of oxygen in CO2? 32. So 1 by 2 will get 0.5. It is a simple whole number ratio, right? Okay, simple ratio, sorry, not simple whole number ratio, simple ratio. Next, coming to law of reciprocal proportion. So if two elements B and C react with the same mass of a third element A, the ratio in which they do so will be the same or simple multiple if B and C reacts with each other. Okay. Next one, coming to Gay-Lussac's law of volume. It is very similar to law of conservation of mass, but it is in terms of volume. So if you have at a given temperature and pressure, the volume of all gases and reactants products bear a simple whole number ratio to each other. So the ratio of the reactants and the ratio of the reactants to volumes is also a simple ratio. Okay. So let us see the next topic, that is your mole concept. So what is there in mole concept? 1 mole of anything, it occupies just 6.022 into 10 to the power of 23 particles. And what is mole? It is a unit of amount of substance, right? Unit of amount of substance. Now, what is there, like how to convert from one? So there are 4 ways of representing the amount of substance. So what are the 4 ways? One is your mass, okay. Another is your number of particles, mass, number of particles. Then another is volume, okay. And the fourth one is number of moles, okay. Now these are the 4 ways by which we can represent the amount of substance, okay. Now see, if we know number of moles and you want to calculate mass, so what you have to do? You have to multiply with molecular mass, okay. Now similarly, if you know the mass and you want to calculate the number of moles, then you have to divide by molecular mass, okay. MM stands for molecular mass. Now number of particles and number of moles. So if we know number of moles and you want to calculate number of particles, then you need to multiply with Avogadro number. And if you have number of particles and you want to find number of moles, you have to divide by Avogadro number. This is called as your Avogadro number. Now from number of moles to volume. So if you have number of moles and you want to calculate volume, you have to multiply with 22.4. And if volume is there and you want to calculate number of moles, you have to divide by 22.4 liter. So this one has to be there under STP condition, standard temperature and pressure condition. What is standard temperature, pressure? Temperature should be like 0 degree, pressure should be 1 atm. Okay. Now let us see the next one, percentage composition, how to find out. So the mass of the element in the compound divided by the molecular mass of the compound into 100. Like for example, a quick one, suppose we take H2O. Okay, what is the percentage of hydrogen in H2O? So the mass of hydrogen is 2, molar mass of water is 18, 2 by 18 into 100. Like this you have to calculate. Next is molecular formula and empirical formula. What is molecular formula? So molecular formula represents the actual number of each individual atom in any molecule. Empirical formula represents the smallest whole number ratio in the constituent atom within the molecule. For example, you take glucose. Okay, glucose actual formula is this one. And empirical formula means you have to take the ratio of all the atoms. So we can cancel 6 ones are 2s are 1s are CH2O. This is the empirical formula and this is the molecular formula. Okay. Now, molecular formula will be equal to empirical formula into N. Okay. Now, molecular weight is equal to N into empirical weight. So just you have to multiply this one. Molecular weight, one more formula is there, is also equal to 2 into vapor density. Okay. Okay. Now, how to calculate empirical formula also we'll see one small example. Suppose you have A, B and C. Okay. Their percentages are given. Suppose this is 20, 30 and 40. So what you have to do, and their molecular masses are Ma, Mb and Mc. Okay. Now, first of all, you have to calculate the number of moles. So number of moles will be given mass by molar mass. So here I will get 20 by Ma, right? Here I will get 30 by Mb and here I will get 40 by Mc. Now, after you get the number of moles, you have to find the simple ratio. Okay, so here what you have to do, you have to divide out of these number of moles, whichever is the smallest one, divide the whole by that number, right? then you will get a simple whole number ratio. Now if this is coming in, like whole numbers are coming, it is fine. If not, then multiply a constant to all the three values to get the final whole number value. Clear? So empirical formula is very easy. Questions are asked from here. Next, if you see limiting reagent, so the reactant which is totally consumed during the course of the reaction, and when it is consumed the reaction stops, that reagent is called as your limiting reagent. How to find a limiting reagent? First you have to balance the reaction. Next, suppose number of moles of A and mass of A is given or mass of B is given. Find the number of moles of A and find the number of moles of B. Okay. Now if number of moles of A by B, okay, this ratio, number of moles of A by B is greater than number of moles of B by A. Okay, in that case, which one will be your limiting reagent? B will be the limiting reagent. Similarly, if this one is greater, right? In that case, A will be the limiting reagent. Clear? Very easy to find out. Next, concentration terms. So we'll see the concentration terms, important one, mass percentage. So mass of the solute by mass of the solution into 100. Mass of the solute by mass of the solution into 100. Next, mass by volume percentage. So mass of the solute, okay, mass of the solute by volume of the solution into 100. Okay. Next, volume by volume percentage. So volume of the solute by volume of the solution into 100. Clear? Next, we have parts per million. So mass of the solute by mass of the solution into 10 to the power of 6. Then mole fraction, we have also already discussed. Number of moles of A by number of moles of A plus number of moles of B is called as mole fraction. Now molarity we have discussed in the solutions chapter. Number of moles of solute by volume of the solution in liter. So that is, we can write it again here. Number of moles of solute means what? Given mass by molar mass into 1000 if the volume is in ml. Now molality will be W by M into 1000 by W, right? So here it is weight of the solute in gram. So here I will write WB, this is B and this is A. Okay. Okay. So finally we have discussed all the important topics, important formulas, and I have also told you which things you must focus in the particular chapter. So only one day is left. So now you can just, if you haven't done any chapter, you can just give a revision to these important topics. And if you have already studied, so focus on these topics once again, review these concepts again, do some numericals from this. Okay. Hello students, welcome back to our channel Diksha Karnataka. So your COMEDK 2024 examination is approaching. So in this video, we will do the complete revision of the inorganic chemistry. Okay, so I'll be covering all the important or inorganic chemistry chapters. I'll be discussing the important topics and the type of questions that is asked also I'll be discussing. So if you watch this video, you can revise the complete inorganic chemistry and you can expect like easily 12 to 15 questions from this all these four topics, because all are high weightage topics. So let us start here, and you will be also getting the PDF of this in our WhatsApp channel. So join our WhatsApp channel. The link will be given in the description section of the video. Okay, so please sit with the notebook and a pen and note down all the important concepts, all the important exceptions, and whatever I tell, just note it down and revise it thoroughly for your COMEDK examination. Okay, so one of the very important video, complete revision of inorganic chemistry. So let us start now with the, so in this video we'll be discussing the four important chapters, that is coordination compounds, DNF block elements, chemical bonding, and classification of elements. Okay, so let us start with the first chapter, that is coordination chemistry. It's a high weightage topic from your PU2, right? So you can easily expect 3 to 4 questions from this chapter. So what are the important topics in this chapter? First, let us see them. So first is your Werner's theory. Okay, so next is your important terms. Will be like questions are asked from these important terms also. Next is nomenclature, very important. Then you have isomerism, then you have bonding theories, and the last is bonding in metal carbonyls. So if by seeing this list I'll say which is the most important thing, then you must mark about Werner's theory, isomerism, nomenclature, and bonding in carbonyls. Bonding in metal carbonyls questions are not asked, but we never know, the question may be asked. So just a very simple concept, we can just revise it once. Okay, so now let us start with the Werner's theory. So according to Werner's theory, in a coordination compound, there are two types of valency. One is your primary valency and secondary valency. So what are the properties of primary valencies? They are ionizable. They can be satisfied by negative ions. And what is, like if someone asks you what is primary valency, it is nothing but the oxidation number of the metal. Okay. Now coming to secondary valencies, these are non-ionizable, satisfied by negative or neutral molecules, and the this is like what is secondary valency? It is the coordination number. Okay. Now how questions are asked? Will they ask you the definition of this? No, they will ask you like, suppose a compound will be given. For example, we have a complex like this, any metal, and then you have CO ligand 4 and then X ligand and then Br3. Then how many ions were produced from here, right? So this complex will be 1 ion and then 3 bromine will be another ion. So total ions produced will be 4. So such type of questions are asked. And the question like about AgCl. So prepare this AgCl concept. Okay. So when they react with, when you react a complex with AgNO3, how many moles of AgCl is produced? And based on that, we can tell how many chlorines were outside the complex and how many chlorines were inside the complex, right? So such type of questions, application based questions are asked from Werner's theory. Now let us go to the next topic, important terms. Which important terms are there? So ligands, there's like this, just for you should know that number of ions or metals that is bonded to the central atom. Now denticity is important. Here you should know the number of ligating groups in a ligand, how many how many sites are there which can donate the electrons to the metal. Now if you see unidentate ligand, your examples are Cl-, H2O, NH3. Didentate ligands, your examples are ethane 1,2-diamine, which we write as EN. Then polydentate ligands, you have the example of EDTA. Okay, so here you should remember EDTA is hexadentate ligand. Okay, next coming to ambidentate ligands. So what do you mean by ambidentate? It means like there will be 2 donating sites in the ligand, but at a time or at least like at one point of time only one will donate. Okay, so your examples are SCN and NCS. Your example is NO2 and NO. So you can just know like questions can be asked which of the following is ambidentate ligand, what is the denticity of these ligands. Okay, so on the basis of denticity you should know the examples. Now coming to coordination number, so the number of ligand atoms donated to the metal directly bonded is called as the coordination number. So from here also you can see cobalt is bonded to 6 ligands, so the coordination number is 6. Now homoleptic and heteroleptic complex, these are very simple concept. So if only one kind of ligands are there, then it is homoleptic. If more than one kind of, so sorry, this one NH3 whole 4 and Cl2. Okay, so if this we have more than one type of ligands, then we call it heteroleptic. Okay, next coming to nomenclature, very important. So I will briefly explain the rules and then we will do 2 examples. You can practice nomenclature examples from NCERT exam. In the chapter it is there, inside the chapter, in the text questions also there, in the in-text questions also there, right? So practice nomenclature thoroughly. Okay, so if I like in coordination chemistry, what you must know is your nomenclature. Okay, so coming to that, first rule is the cation should be named first and then the anion. So whether cation is a complex or anion is a complex or cation is auxiliary ion, doesn't matter. First cation, then anion. Now the ligands are named in the alphabetical order. Okay, so in the complex, first the ligands will be named and then the metal will be named. Name of the anionic ligands in ending it with O. Those of the neutral and cationic ligands are same expected for water, amine and carbonyl for CO and nitrosyl for NO. Okay, so what does it say? The ligands, okay, the name of the ligands will generally end with O for negative anionic ligands, and for neutral ligands there are special names, like for water it is aqua, for NH3 it is amine, for CO group it is carbonyl, and for NO group it is nitrosyl. Okay, okay, now coming to this one, if more than one ligands are there, then what prefix we should use? Mono, di, tri, like that we have to use. Now if the name of the ligand contains more than one name, then we have to use bis, tris and tetrachus for giving you the number of ligands present. Next rule is Roman numeral in the parenthesis. So after the metal is written, its oxidation state is written in Roman numbers in brackets. Okay, which type of brackets? Like this bracket. Okay, next, if the complex is a cation, so I told you complex can be cation also, can be anion also. So if the complex is a cation, then the metal is named as same as the element. For example, if the metal is iron, then it will be iron. The metal is cobalt, it will be cobalt. But if the complex is anion, okay, the anion part is the complex, then the metal name should end with ATE. Okay, that is very important. Now let us see one example here. You can see this compound. Okay, so this, in this case, the complex is your cation. Okay, so here first you have to name the ligands. So we have here 3 aqua and we have 3 amine group, right? So based on your alphabetical order, first amine will come. So triamine, triaqua. Then since complex is the cation, the metal name will remain as it is. So chromium. Okay. Then 3. Then we have chloride. Okay. Here this should not be written as trichloride. For auxiliary ions, there should not be any suffix or prefix required. Now if you come to this one here, this is a ligand with more than one name, ethane 1,2-diamine. So 3 are there. So we have to use the word tris. Okay. Tris ethane 1,2-diamine, cobalt, then oxidation state, and then sulfate. Here also you need not write trisulfate, should not be written. Okay. Now coming to isomerism, next important topic. So isomerism is of two types. First is your optical isomerism and then is your structural isomerism. In optical isomerism, we have geometrical isomerism and stereoisomerism. Geometrical isomerism, you know, cis and trans, and in stereoisomerism, enantiomers are there, right? Now in structural isomerism, we have linkage, ionization, coordination, and solvent isomerism. Very, very important topic. Okay, now let us first see geometrical isomerism. So in geometrical isomerism, if you see, if the same ligands are on the same side, we call it cis. If the ligands are on opposite side, we call it trans. Now you can see here, this is for coordination number 4. Okay. Now if coordination number 6 is there and the ligands are of the form like Ma4B2, you can see if the two chlorines are opposite, it is trans. If two chlorines are lying in the are not opposite to each other, this is the cis geometry. Next, coming to this one is very important, Ma2B2 type. Okay, where this is a bidentate ligand. Okay. In this case, you must remember the cis form of this one is optically active. Okay, cis form of this one is optically active. We'll see that also. So cis form, you can see two chlorines are opposite to each other, that is trans form, and when the two chlorines are nearby to each other, that is your cis form. Okay. Now coming to the next question, next topic, that is stereoisomerism. So if you have the mirror images are non-superimposable mirror images, then they form enantiomers, right? So you can see here, this is like a form COEN whole 3. So these two are non-superimposable mirror images, so they will be our enantiomers. And now if you see this one, AA2B2 type, I told you, the cis form will be your optically active, trans form will be will not be optically active. Okay. Next, seeing the next one, structural isomerism. So here you should know what is linkage isomerism. For linkage isomerism, we need ambidentate ligands. Okay. So if NO2 is there, what is its linkage isomer? So CO NH3 5 ONO Cl2. Okay. Now coming to coordinate isomerism, in coordinate isomerism, what happened? Ligands get exchanged. So what will be the coordinate isomerism for this one? CO, I'll write CN whole 6 and we have CR NH3 whole 6. Okay. Now coming to ionization isomerism, in ionization isomerism, when you put the compound in the water, if different ions are produced, then we call it as ionization isomerism. Now in this case, what we'll get this complex as one and Br minus as another ion. Here we'll set this complex as one and sulfate as another ion. So formula is same, but in water we are getting different ions, so we call it as ionization isomerism. In solvent isomerism, very easy, water should be there as a solvent, right? So you can see here we have water and here this water can come out and Cl3 can go out. So water can be coming like inside the complex and outside the complex, you can interchange, then we'll get a solvent isomerism. Okay. Okay. Now coming to bonding theories. Okay. So what were the different theories that describe the coordinate bond or coordination bond? So first theory that came was your valence bond theory. According to valence bond theory, what happened? The n-1d, ns, np, ns, np and nd. Okay. So these orbitals can participate in the bond formation. Okay. So these orbitals undergo hybridization to yield a set of equivalent hybrid orbitals such as octahedral, tetrahedral or square planar. So here are the hybridizations. You must remember, if the coordination number is 4, we have two types of hybridization, that is sp3 and dsp2. So you can see here there are two types of combination. I'll write. See, you can see if we have n-1, so I'll write here. See, for sp3 we need ns and np orbitals to combine. For dsp2 I need n-1d, ns and np orbitals to combine. For sp3d2 we need ns, np and nd. Okay, and for sp3d, now same for sp3d2, but for d2sp3 we need n-1d, ns and np orbitals. Okay, so these are the geometries. Now what are the geometries produced? You can see for coordination number 4 we have two types of geometry, tetrahedral and square planar. For sp3 it is tetrahedral, for dsp2 it is square planar. For coordination number 5 sp3d it is trigonal bipyramidal. For coordination number 6 sp3d2 octahedral, d2sp3 is also octahedral. So whenever you are using n-1d we call it inner orbital complex. Okay. Okay, now let us see. These are the 4 examples of the compounds that are given in your NCERT book. Okay, so please remember these examples thoroughly so that in exam you did not have to calculate and find out everything. So for cobalt NH3 it is a strong field ligand. So that is why we will get D2sp3 hybridization. Shape will be octahedral since the coordination number is 6, and since it is a strong field ligand, pairing of electron will take place. It will be diamagnetic, right? Now if you see here, next one is COF6 3-. It is a weak field ligand, right? But coordination number is 6. So we will get octahedral geometry. Weak field ligand means outer orbital complex sp3d2. So I'll write here, this is inner orbital, this is outer orbital. Okay. Next, the magnetic property will be paramagnetic because it has unpaired electrons. Now if you see NiCl4 2-, this is sp3 hybridization. Again, this is outer orbital complex, tetrahedral and paramagnetic. And in NiCN4 2-, so there is no concept of outer because d orbital is not involved. Here it is dsp2 square planar and diamagnetic. Okay, next one we'll see. So what does crystal field theory tells us? So next, after valence bond theory, the next bonding theory is crystal field theory. So in crystal field theory, this one a question was asked. You should know metal ligand bond is considered to be ionic arising purely from electrostatic interactions between the metal ion and the ligand. Okay, so this point you should remember. According to this crystal field theory, the metal ion and ligand has an electrostatic force of attraction, because of which we consider them as an ionic bond. Okay, next, so what happens when ligand approaches the metal, the d orbitals split to reduce the repulsions. So splitting of d orbitals depends on the strength of the ligands. Okay, the splitting can be more, splitting can be less, depending on the ligands. Okay, now coming to this, so we have crystal field theory, crystal field splitting in octahedral. So what happens? First, initially all the 5 d orbitals are degenerate. Now when the ligands approaches to reduce the repulsion, they go in this way. Okay, so 3 orbitals come here and 2 orbitals go down. You can see in the diagram here, if it is visible, these 3 orbitals are called as your T2g orbital, dxy, dyz and dxz. Okay, so what are that? I'll write here dxy, dyz and dzx. Now similarly, out of 5, 3 went down, so 2 will be up. So these 2 are your dx square minus y square and dz square, right? You can see here. Now you should also remember the values. Okay, so how much decrease is there? So how to remember? See, total there are 5 orbitals. Okay, so here 3 is there, 3 has come down, so this will be minus 2 by 5 delta O, and here there is 2, so it will be 3 by 5 delta O. Okay, so please remember, this is plus, this is minus. Okay, next is your crystal field splitting. Okay, so this is the same one which we have explained. Next is your crystal field splitting in tetrahedral complexes. So if you see in tetrahedral complex, the opposite will happen. So here 5 orbitals were there, right? After this one, 2 will go down and 3 will go up. And here we do not use the word T2G. G is not used. So it is only called T2. Sorry, this one is called E and this one is called T2, right? So here the orbitals are your dz square and dx square minus y square, and here it is dxy, dyz and dzx. Okay, so crystal field splitting in tetrahedral is not much asked in the question, but in octahedral complex the splitting is very, very important. Okay, now coming to, okay, here I want to discuss one more thing about the how to write the electronic configuration in strong field and weak field. So very important, see here, if it is a strong field ligand, okay, then splitting will be more. Okay, splitting is high, and pairing of electrons will not take place. Sorry, pairing of electrons will take place. Okay. Now for D1, D2, D3, there is no configuration change whether it is a strong field ligand or it is a weak field ligand. But for D5, D4 to D7, you have to be very careful. Now we will discuss that. Suppose D4 is there, okay, strong field ligand and weak field ligand. So here you imagine, here we have strong field ligand, so splitting will be more. Okay, so we'll draw here. In strong field ligand, the splitting will be more. Okay, and in weak field ligand, the splitting will be less. Okay, so now this is strong field ligand and this is weak field ligand. Okay, so now we have here 3 orbitals, here 2, and here also 3, and here we have 2. Now D4 is there, right? So how you should not remember it, you have to understand it. D4 is there means 4 electrons, 1, 2, 3. It cannot go there because it requires more energy, so it will pair up here. So D4 in strong field will be T2G4, right? But in weak field, what will happen? 1, 2, 3. It is very less energy gap. It can easily go there. So here it will be T2G3 and EG1. Now similarly D5, if you see, 5th electron will also come here. So we will get T2G5, and for here we will get T2G3EG2. Now if you see D6, again the 6th electron, 5th electron came here. 6th electron will come here. So we will get T2G6. Now for weak field ligand, if you see 1, 2, 3, 4, 5 was there, and now 6th electron will come here. So we will get T2G4 EG2. Now for D7, if you see, already T2G6 has been there. Now T2G7 will come here, right? So 1, 2, 3, 4, 5, 6, 7th electron has no other option. It has to go there. So we will get here T2G6 EG1. Now if you see for this one, 1, 2, 3, 4, 5, 6 and 7 I can fill here. So I will get T2G5 and EG2. Okay. So this D4 to D7 configuration for strong field and weak field you have to remember. Next, color in coordination compound. So very basic thing you have to remember. There is no like the only thing you have to remember, if there is unpaired electron, okay, if there is unpaired electron then it will be colored, okay, and if there is no unpaired electron then it will be colorless. How will you know whether it is colored or not? For that you must know the configuration. Okay, now the color is due to DD transition. Okay, next coming to bonding in metal carbonyls. I told you this is not a very important topic, but we can understand in a very short way. So first of all, there is a metal carbon bond. So there is a metal carbon bond. Okay, so carbonyl donates electron to metal. That is what is done by every ligand. Every ligand donates electron to the metal. What special is here? The speciality is the metal also donates back electrons to the carbon, right? So the metal carbon bond in metal carbonyls possess both S and P character. So this is sigma bond and this is pi bond. Okay, now the MC sigma bond, the sigma bond which is formed is due to the donation of electrons from the ligand to the metal, is formed by the donation of lone pair of electrons on the carbonyl carbon into the vacant orbital of the metal. Okay, now MC pi bond, okay, this pi bond is donated by metal to the carbonyl, is formed by the donation of a pair of electrons from a filled d orbital of metal into the vacant anti-bonding orbital of carbon monoxide, right? So you can see here this one, okay, here sigma bond is from carbonyl to metal and pi bond is from metal to carbonyl. So anti-bonding orbital is used. Okay, so these were the important topics in coordination chemistry. So what you have to focus, only 1 day or like 1.5 days left. So focus on your nomenclature, isomerism and d orbital splitting. These are the 3 important topics that you must clear. Okay, so now let us go to the next important topic, that is D and F block. So here we will be discussing the important configurations, important trends, important exceptions, okay, and like the physical properties, different D and F block, that they show different physical properties. What are the reasons for that? The questions can be asked from there, right? So let us quickly go through this chapter. What are the topics? First, electronic configuration. Okay, This is very, very important. Okay, without doing electronic configuration, you cannot solve even a single easy question from this one. You need to know the magnetic property. You need to calculate the color, whether it is color or colorless. Everything you can do only if you know the electronic configuration, right? So please remember scandium to zinc, all the electronic configuration, very, very important. Okay. Next, important trends we will discuss. Next, physical properties, and why this physical, what are the reasons for these physical properties, and then we'll discuss about the F block elements. Okay. Okay, so the electronic configuration is already there, so nothing to discuss here. You must remember here. So just I'll tell, chromium and copper has a special electronic configuration. 3d4 4s2 was the expected value, but due to the half-filled electronic configuration, what happens? We get 3d5 and 4s1. Similarly, for copper, we have 3d9 and 4s2 is the expected electronic configuration, but the observed is due to 3d10 4s2, so that it becomes a fully filled d orbital. Okay, and we know fully filled electronic configurations are very stable. Next, one more thing here is, what is the general electronic configuration? n-1 d 1 to 10, ns 1 to 2. Okay, so n-1 d 1 to 10, ns 1 to 2. Okay. Next, so coming to the first trend, that is your atomic radius. So first of all, atomic radius decreases rapidly from column 3 to 6. So that is from your up to scandium to chromium, the atomic size decreases. Then it remains constant from 7 to 10. So you can say almost from chromium to nickel it is constant, and then it starts rising from 11. So I can write here from scandium to chromium, then from manganese to nickel, and then copper to zinc, it increases. Okay. Okay. So now what is the reason for that? Here what happens? Here the effective nuclear charge is more powerful. Okay. Here what is like the effective nuclear charge, okay, and the repulsion, the d electron repulsion, both are d electron repulsions are balanced out. And in the last one, if you see, the d electron repulsions are more dominating than the effective nuclear charge. So if you can understand, effective nuclear charge, okay, wants to try to pull the electron towards itself and wants to reduce the size of the atom. And since as we go from the period, the d electrons are getting filled, so there will be inter-electron repulsions between the d electrons, so that wants to expand the size. So there is a conflict between them. So when we are going initially up to, you can say up to chromium, the effective nuclear charge is the winner. So what is its effect? It wants to reduce the size, right? So till chromium it will reduce the size. Now if you go in this region, you can see there is a, like, this region is almost constant, right? The size is almost constant. So at this point what is happening? The inter-electronic, the d repulsions of the d electrons, and we have this effective nuclear charge, they're almost balanced out on each other. Now as we go around copper and zinc, d10 electrons, right, they're completely filled, more repulsion, so they are more dominating and the size keeps on increasing. Okay, next we'll go ionization energy. So ionization energy increases with the increase in the atomic number up to Fe. So as the size decreases, the ionization energy will increase. Okay. Next, in cobalt and nickel, the increasing sharing of d electron compensates for the atomic number increase, resulting in the decrease in the ionization energy. So again, as we say, from cobalt to nickel, as the d electrons start filling, so the effective nuclear charge decreases. So that is why the ionization energy decreases. Then again, copper and zinc shows increasing ionization energy, because here it is completely filled d10 orbital, right? So removing of electron from completely filled orbitals is again very difficult. So that is why from nickel to copper it keeps on increasing. Okay. Next, metallic character and hardness. So the d block elements have the metallic character like high tensile strength, malleability, ductility, electrical and thermal conductivity, metallic luster, crystallize in BCC. So these are basic things, we need not focus here. Here it is important. They are very hard and have high enthalpy of atomization and low volatility, except copper, right? So copper is having 3d10 electronic configuration, so it doesn't have like metallic bonding is very weak, so that is why it is enthalpy of atomization is very low. Now hardness increases with the number of unpaired electrons. So more is the number of unpaired electrons, more will be the metallic bonding, and more will be the hardness of the metal. Now as you see, chromium, molybdenum and tungsten, they are having the highest number of unpaired electrons, so they show the highest, like they are the hardest metals, and they also have very high melting point and boiling point. But if you see zinc, copper, zinc, cadmium and mercury, they are having like no unpaired electrons are there, so no metallic bonding, and that is why they are very soft metals. Okay. Next is your oxidation state. So if you see, so they show variable oxidation state due to the participation of n and n-1 d electrons. So why both the orbitals participate? Because of less energy difference. Okay. Now the higher oxidation states will be stabilized by fluorine and oxygen. The lowest oxidation shown is +1. Highest oxidation state in the entire 3D elements is shown by +8, that is your osmonium. Then this you have to remember, very important, which are your basic oxides, which are your amphoteric, and which are your acidic oxides. So if you remember, like a general thing, if oxidation state is low, then it is basic. Okay. If oxidation state is somewhere in medium, then it will be amphoteric, and then oxidation state of if is very high, then it will be acidic in nature. Okay. So you have to remember amphoteric, especially remember all the examples, very important, because they will be asking like which of the following oxides are amphoteric or basic or acidic. So you have to remember as many examples as you can. Okay. Now coming to the next one, electrode potential. So depends, so here you have to know electrode potential like depends on what 3 factors. It depends on sublimation energy, ionization energy, and hydration enthalpy. Next, one more thing, copper is the only element with a positive electrode potential of 0.34 volt. So this one also you remember. Okay, next coming to physical properties. Okay, we discussed about the chemical properties. Now some physical properties of transition elements. So first is density. Okay, so density increase remains almost the same and then decreases along the period. So if you know, density formula is what? Mass by volume. Volume we can, since it is sphere, we can like 4/3 pi r cube. Okay, so density is inversely proportional to radius. So initially if you see, the radius was decreasing. If radius was decreasing, then if radius will decrease, then density will increase. So initially it decreases, then radius remains constant, density remains constant. Then towards the end radius increases, so volume will increase, so density will decrease, right? That is what happening. Now here something you can remember, scandium in the third 3D series. Okay, scandium has the lowest density and copper has the highest density. Okay, and then copper has the highest density. It has different reasons, like, but you should remember the elements. Then osmonium and iridium, these are the highest density among all the d block elements. Okay, next we come about melting point and boiling point. This is also very important to understand. If the metallic bonding is very strong, melting point and boiling point will be high, and metallic bonding depends on the number of unpaired electrons. So chromium, molybdenum and tungsten have very high melting point because they have stronger metallic bonding. Okay, now manganese and technetium, what happens, although they have unpaired electrons, but they are half filled configuration, right? So they are very stable, they are not involved in metallic bonding, so they have low melting point and boiling point. Now zinc, cadmium and mercury, because they have no unpaired electrons, they cannot undergo metallic bonding, so they also have the lowest melting point and boiling point in their respective series. Okay. Now coming to colored iron. So this is very easy concept. Due to DD transition it happens. If there is no unpaired electron, they will be colorless. So questions are asked, which of the following are colored, which of the following are colorless. So you can easily use this concept and find it out. Next is, we know that this d block elements can form complex. So what are the reasons for that? They can know small ionic size because they have high charge and they have availability of d orbitals. So you should know these reasons. Like question can be asked like 3-4 factors will be given. Which factor contributes for complex formation, right? So you should know these basic things. Next, similarly, catalytic property is due to the vacant d orbital and they can exhibit variable oxidation states. Alloy formation, this is because of all the transition elements have almost similar atomic radii, so it is easy to mix them. Now interstitial compounds, so they so whenever you have like crystal is there, there will be some spaces or voids will be there, and that voids are filled with non-metallic items. Like here we have nitrogen, hydrogen, oxygen, carbon. Okay. So when they enter and they form interstitial compounds. Okay, next is very important, this one, important compounds in the compounds in DNF block. So first is your potassium dichromate, that is K2Cr2O7. So if you see here, the starting material, you should remember, many times this question is asked, that it is prepared from chromite ore. Okay, the formula and the name, iron chromite ore is there. So this one is converted to sodium chromate, then sodium chromate is converted to sodium dichromate, then sodium dichromate is converted to potassium dichromate. Exact relation, the equation no need to remember, just remember the starting materials and the products of each step. Okay, next is your structure. So here question is asked like, are all the bonds equivalent or not in dichromate, right? So you can see that these three bonds undergo resonance, so they are equivalent, but these CRO are not equivalent, right? And the chromate ion and dichromate ion structure. Next, we'll go to the next important compounds, that is KMnO4. So here also you can see the preparation, manganese oxide, KOH. So the starting material is manganese oxide and it gives you potassium manganate, and then from potassium manganate we get potassium dipermanganate. Okay, so these four structures you should remember, or the name you have to remember. Okay. Next, coming to, yes, lanthanides, very, very important. Electronic configurations are there, but I'll recommend or I'll suggest you to remember all the electronic configuration, but still if you have no time or you're not able to, certain electronic configuration that you must remember is your lanthanum, cerium, okay, and then europium, gadolinium, and then you have the ytterbium and lutetium, and yes, these elements, electronic configuration, please remember. Okay, very, very important electronic configurations. Now, so what is the general electronic configuration? Here also it is written 4F1 to 14, 5D0 to 1, and 6S1 to 2. Okay. Now coming to the oxidation state. So this is very important slide. So common oxidation shown is +3. Okay. But in certain cases it can show +4 and +2 also. So what are there if we can get a noble gas configuration? So if you see cerium, okay, cerium has 4F1, 5D1 and 6S2. So if it loses these all electrons, it will have a noble electronic configuration of xenon, right? So that is why here it can show +4 oxidation state. Now it can also show +2 oxidation state if it is getting a half-filled configuration. So europium and terbium 4+. So if you see europium, if you see 4F7 and 6S2, so +2 will give you 4F7, right? Which is plus 4F7, which is your exactly half filled. So that is why it can show. And we have here 4F terbium is 4F9 and 6S2. So if it loses 4 electron, 2 electron will go here, 2 electron will go here, we will get 4F7. This is also, in that case also they can show +2 and +4 state. Now next one is your YB2+. If it is a fully filled level is also there, then also it can show. But general oxidation state is +3. In certain cases it can show +2 and +4. Okay. Now let us see the next one. What about atomic radius? So we know from lanthanum to lutetium that lanthanide contraction is there. Why? Due to the poor shielding effect of 4f orbitals. So the size increases steadily. Okay. Now what are about colored compounds? They are silvery white in color. They are all colored compounds due to FF transitions. Now this is again very important slide. Lanthanide contraction and its consequences. We have already seen the causes. What is the consequences? The atomic size, okay, of the fifth period and sixth period elements are almost same. So example you have to remember zirconium and hafnium and Nb and Ta. Okay. Next one is your due to this what happens? Due to this they have the similar chemical properties, so it is very difficult to separate them. And the last one is their basic strength. This is very important. Lutetium is the last one. Okay. So effective nuclear charge is very high. The electron pairs are very tightly held. It is very difficult to donate. So it will have the least basicity. Whereas lanthanum size or the effective nuclear charge is less. Its lone pair can be easily donated. So its basicity is less. Okay. It is high. Okay. So now let us see the next chapter from your PU1. This is a very high weightage topic and very easy question. The questions are asked from a certain section of the chapter, not the entire chapter, but we'll discuss the whole chapter. But I'll also be telling you which chapter or which topics you must focus, from where the questions are must asked. Okay. So let us start with the next chapter, that is chemical bonding and molecular structure. Okay. So first let us see the topics here. There are a lot of topics in this chapter, but again the important topics are very few and very scoring topics. First is your Lewis structures, how to draw the Lewis structures. Second, octet rule and its exceptions. Then we have formal charge calculation, ionic bond, covalent bond, Vesper theory, Fazan's rule. Then we have dipole moment. Then we have hydrogen bonding, valence bond theory, and then we have hybridization, and then bond parameters, and then molecular orbital theory. I'll be telling you now which are the most important one. So first important one is covalent bond. Formal charge calculation, just we'll practice some formulas and we can do it. Dipole moment is not very important, but sometimes questions are asked like which has a net dipole moment, so you should know where it is cancelled and where it is not cancelled. Then hydrogen bonding, also one or two questions have been asked like intermolecular and intramolecular hydrogen bonding. Valence bond theory is as hybridization is important. Valence bond theory, nothing much is there. If you know Vesper theory, then just have to understand the concept. Bond characters is important. Molecular orbital theory is very important. Okay. Now let us start with Lewis structure. So just what is Lewis structure? Drawing, you represent the bonds with a line, the lone pairs, the non-bonded electrons with the dot. So we calculate the total valence electron, and then we assume that every element has an octet rule, satisfies the octet rule, and then we fill the electrons, right? That is what is Lewis structure. Now octet rule, what is it? According to octet rule, every element wants 8 electrons in its valence shell to gain stability, right? Now there are some exceptions to this that you should know. So that species like which have odd number of electrons, NO and NO2, they cannot, their octet is not satisfied. Then we have incomplete octet and we have expanded octet. So those elements where the number of electrons of a central atom is less than 8, and there are some elements or some compounds where the number of electrons of the central atom is more than 8, right? So expanded octet is more than 8, incomplete octet is less than 8. So if you see this one, BCl3, okay, boron has your 3 electrons in the valence shell, right? So it forms bond with 3 chlorine. So if you see, there are total 6 valence electrons for boron, whether it should be 8, right? So that is incomplete octet. Now if you see here SF6, right, sulfur has 6 electrons. So we'll draw like this, SF. So 6 valence electron form 6 bonds with 6 fluorines. So the total number of electrons we get is 12, right? So you should remember second period elements, okay, will not show expanded octet. Will not show expanded octet because they do not have empty d orbitals. The third period elements, you can see phosphorus, sulfur, these are all third period elements. They can show expanded octet because they have availability of d orbitals, okay? Now let us go next. Formal charge calculation, very, very important. We'll do one example on this one. For example, ozone structure, if you know, resonating structure of ozone is this one, right? So your task is to calculate the formal charge on all the oxygen, O1, O2 and O3, okay? So we don't know this one, we'll draw. So here you can see 1, 2, 3, 4. So 5, 6, 7, 8. 8 electrons are satisfied. 1, 2, 3, 4, 5, 6. So 7, 8. And here 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now formal charge calculation formula is for every element the total number of valence electron. Okay. Total number of valence electron minus the total number of lone pair of electrons. How many electrons are there in the lone pair? And then plus to the total number of bonds, means this is negative only, this total you have to add and then subtract from the total valence electron. Now we will do for this one, for O1. Oxygen has how many valence electron? 6, right? So it will be 6 minus, then you see how many lone pair of electrons are there. 1, 2, 3, 4, not pair. How many electrons you have to calculate? So 6 plus 2, that is 4, okay? Then here we have how many bonds are there, not bond pair of electrons, only bond pairs, So we have 2 bonds, right? So this one we will get 0. So formal charge of this oxygen is 0. Okay. Now let us calculate for O2. This is not oxygen, okay, second oxygen. So there are 6 valence electron minus. How many lone pairs of electrons are there? 2, okay. Then how many bond pairs are there? 1, 2 and 3. That is 6 minus 5, that is 1. So we will get plus 1 here. Now if we have O3, you can see 6 valence electron minus. How many are there? Total number of lone pair of electrons, that is 6. And how many bonds are there? That is 1. Okay, 6 minus 7 we have minus 1. Okay, plus 1. So here it is 0 plus 1 minus 1. Okay, that is how you can calculate the formal charge. Now coming to ionic compounds, very shortly we can discuss how the ionic compounds are formed by the transfer of electrons, ionization energy. So the metals has to release one electron, the non-metal has to gain one electron, and when they combine, lattice energy is released. Now what are the conditions? So ionization energy of the cation should be low. Very easily we should be able to release the electron or remove the electron from the cation, and high electron gain enthalpy of the anion and high lattice energy, right? So means the anion should be able, or the non-metal should be able to gain the electron, it should become stable, it should release more energy, and when the cation and anion combine, there should be loss of energy so that the molecule is stable, so lattice energy should be high. Okay. Now coming to covalent compounds, again what is covalent compounds? It is formed by the sharing of electrons. The electrons which participate as called bond pairs, which do not participate as coral are called as lone pairs. This is very important because Vesper theory is completely based on lone pair bond pair, right? Okay. Now coming to Vesper theory. So what does Vesper theory says? The shape of the molecule is determined by the repulsions between all the electron pairs present in the valence shell. These electron pairs can be bond pair, can be lone pair. Okay. So the order of repulsions you should remember: lone pair, then lone pair, bond pair, and then we have bond pair, bond pair. Okay. Now repulsions among the bond pairs is directly proportional to the bond order and electronegativity difference between the central atom and the other atoms. Okay. Yes, this is the topic from where definitely every year we get questions. A lot of questions are asked. This table, everyone, whether you study chemical bonding or not, this table everyone should remember and go to the exam. Definitely a question comes from here. The structure and the geometry you must remember. So if electron pairs are 2, then it will be definitely 2 bond pairs. The shape is linear, geometry is linear, and the example you can remember. Next, coming to 3 electron pairs, it has 3 bond pairs and 0 lone pair. Then we'll get trigonal planar. Shape is also trigonal planar. Examples are BCl3 and BF3. Now, if we have 2 bond pairs and 1 lone pair, then it is a bend shape. Example is SO2. Then we have 4 lone pairs and 4 bond pairs and 0 lone pairs. Then it is tetrahedral, CH4, and then 3 and 1 you will have pyramidal. 2 and 2 you will get bent. Now, if you have 5 electron pairs, what are the possibility? 5, 0, 4, 1, 3, 2, 2, 3, right? So here we'll get trigonal, bipyramidal, seesaw, T-shape, and linear. This is important. This is important. Square pyramidal, square planar. Okay, these are all important geometries. So please remember them. Then for coordination number 6, we have 6, 0, 5, 1, and 4, 2. This table, please take a screenshot. Remember, it is there in the NCERT book also. Very easily available and very important table. Okay. So this is just I'll discuss, like I have discussed, you have to remember the examples properly. Okay. Now next one is your Fazan's rule. So here the questions are asked, like they will give you the compounds and you have to arrange them in the increasing or decreasing order of your like covalent nature. Okay. So for more, if the covalence is favored by, when we can say that the molecule is more covalent, if the cation size is smaller, anion size is larger, and the cation or anion, anyone should have the more charge should be more. Okay. Like for example, if we take for example NaCl, okay, CaCl2 and MgCl2. Okay. Now if you see here, first of all the anions are same, you have to check the cations, right? So cation size should be smaller. So if you see, they are in the periodic table like this: sodium and magnesium and then calcium. So the smallest size is of magnesium, right? So magnesium will be the least covalent nature, or the compound with the least covalent, with the most covalent character. Okay. So like this you can find the order. And now coming to dipole moment. So dipole moment, you know the formula is Q into D. Okay. Dipole moment formula is Q into D. And then what else is there? Here you have to know the units, that is D by units. And then there's more important here, formula based questions are not asked, like whether the compound is having a net dipole moment or not. Like for example, they'll ask you 1,4-chlorobenzene and 1,2-dichlorobenzene. Okay. This question was asked in the previous year also. Okay. Now if you see, here the dipole moment is in this direction, this is in this direction, equal in magnitude and opposite in direction. So they will cancel each other. Now here what happens? It will be having a net dipole moment. So this compound is polar, or you can say have a net dipole moment. This is non-polar compound even though it has a polar bonds. Okay. Next is your hydrogen bonding. So for hydrogen bonding, what is the what are the conditions that has to be there? So the hydrogen must be attached to the electronegative atom, okay, like oxygen, fluorine and nitrogen. And there can be like two types of hydrogen bonding. One is intermolecular and intramolecular. Here you have to remember, if it is intermolecular hydrogen bonding, then the boiling point will increase because the molecules are strongly attracted to each other. We need more energy to break the bond. So in that case, the boiling point will increase. And if we have intramolecular hydrogen bonding, in that case, the boiling point will decrease. Okay, like two compounds are given in one, like for example, we have orthonitrophenol, okay, and paranitrophenol. Okay, now if you see here this one can have ortho hydrogen, like intramolecular hydrogen bonding, and here we can have intermolecular hydrogen bonding, right? So now if intermolecular hydrogen bonding will be there, then it is difficult to separate them and the boiling point will increase. So in this case, the boiling point will reduce. In that case, the boiling point will increase. Okay, so next is your valence bond theory. So what does the valence bond theory says? A covalent bond is formed by the overlapping of valence shell atomic orbital of the two atoms having the unpaired electrons. So when the valence orbitals combine, okay, then that is called as valence bond theory. Sigma bond is formed by head-on overlapping and pi bond is formed by sidewise overlapping. Here you should know sigma bond is formed from SS overlapping and SP overlapping. Pi bond is formed from PP overlapping. PX PX and PY PY, and here we consider as SPZ. So there is no hard and fast rule, but as a convention we take that PZ orbital is used for sigma bond formation, but not, no, it's like just a convention used. Okay. So how it looks, SS will look like this, SP will look like this, and we have PX. PX means it will look, so PX can also form sigma bond. Okay. Then if we have one more, we can have here one more sigma like this. This will be forming your pi bond, and we can have like this. This can form your two pi bonds. Okay. Now coming to hybridization. So according to hybridization, what happens? The valence atomic orbitals mix and form new hybrid orbitals. So number of atomic orbitals, this is very important, formed is equal to the number of orbitals taking part in the hybridization. So in your syllabus, you have three important hybridization, sp3, sp2 and sp. sp will give you tetrahedral, sp3 trigonal planar, and sp is linear. Here how questions are asked, they will give you a structure, carbon generally, and they will ask you to tell you the hybridization of each carbon, right? So like for example, so how you should know? For determining the hybridization, you should know that number of bonds, number of sigma bonds plus number of lone pairs. Okay. So what number is that coming? If it comes out to be 4, okay, then hybridization is sp3. If it comes out to be 3, then hybridization is sp2. If this comes out to be 2, then hybridization is sp. Okay. So for example, we have a structure like this. We can draw one structure like this. Okay. And you have to tell the hybridization of each carbon. Now you see if this first carbon has 3 sigma bond, 3 sigma bond. 3 sigma bond means hybridization is sp2. This one is having also 3 sigma bond. So this is also sp2. This one is having 4 sigma bond, so it is sp3. Okay, like this you have to calculate. Next, coming to bond characteristics, this is very important. Here we have to discuss also how to find the bond order with a trick. Okay, so first of all, bond strength means what? Higher the amount of energy required to break a bond. Okay, now higher the bond order, higher will be the bond strength. So how to calculate the bond order? I'll tell you a trick. You have to calculate the total valence electron. Okay, total valence electrons. If the total valence electrons is 14, then the bond order should be 3. Okay, bond order. Sorry, not total valence electron, it is total electrons. Okay. Okay. Now you have to, when you go on the other side, this value will decrease by half. When you go above 14 or below 14, the value will decrease by half. So 14 to 15, it will become 2.5. If 16, it is 2, 17, 1.5, 18, 1. 13, again 2.5, 12, 2, 11, 1.5, 10, 1. Now questions are asked, for example, you have to compare for N2, N2 plus and N2 minus. Calculate their bond order or bond length can also be asked. Now if N2 is there, N2 valence total electron is 7, like atomic number is 7, 7 plus 7, 14, so N2 bond order will be 3. Now N2 plus means 14 minus 1 we will do 13, so 13 bond order will be 2.5. N2 minus means, so I'll make it N2 2 minus for example. So then what will there? 7 plus 7, 14 plus 2, 16, so 8 bond order will be 2. Then what is the bond order? N2, N2 plus and N2 2 minus. And next you have to see is very important, higher the bond order, lesser will be the bond length. So if the same thing we want to arrange in the bond length order, it will become opposite. N2 will have the least one, N2 plus and then N2 2 minus. Okay, so this is important, this trick you remember. Questions are asked from bond order, especially O2, N2, these are commonly asked. So just prepare this formula, try these questions, it will be very easy to solve and scoring. Next we come about molecular orbital theory. So according to molecular orbital theory, it is the linear combination of atomic orbitals. Okay, atomic orbitals are considered as wave functions here. So waves can have constructive interference and destructive interference. So if it is constructive interference, we get bonding molecular orbital. If it is destructive interference, we get anti-bonding molecular orbital. Next point you should remember is anti-bonding molecular orbital have higher energy than bonding molecular orbital. Now the electronic configuration you should remember, if it is like 14 or less than 14 the total number of electrons, then sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px, pi 2py, sigma 2pz, pi star 2px, pi star 2py, sigma star 2pz. Now if the number of electrons is like greater than 14 for O2, like 16 electrons are there, then the electronic configuration will change and we'll get sigma 1. So everything is same. Here what happens? This one interchanges. Okay, we will get first sigma 2pz, then pi 2px equal to pi 2py. Other rest part is same. Okay, now from this one you can also calculate bond order. Bond order is half of number of bonding electrons minus number of anti-bonding electrons. From here questions are also asked to calculate the paramagnetic nature and the diamagnetic nature. Okay, so now we will see one small example for this one. Suppose you have N2. Okay, so N2 has 14 electrons. So we have sigma 1s, sigma 1 star 1s, sigma 2s, sigma star 2s, right? After that it will come pi 2px, pi 2py, right? So we can have pi 2px and pi 2py. So and then we have sigma 2pz. Now you see 14 electrons, so I'll fill here 2, 4, 6, 8, here 9, 10, 11, 12, 13, 14. Okay, so now how to calculate the bond order? Bond order will be bonding orbitals. How many electrons are there? These, the ones with star are called as anti-bonding and the one without star are bonding orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and we have 4 electrons here by 2, right? So that is 6 by 2, that is 3. Bond order is 3. Now how to tell magnetic properties? There is no unpaired electron here, right? So that is why it is a diamagnetic. So if there is no unpaired electron, then it is diamagnetic, and if there is unpaired electron, okay, then we call it paramagnetic. Okay. Now for example, we will write another example we'll take for oxygen molecule. Okay, so for oxygen the order will change here. So I will get here sigma 1s2, okay, sigma star 1s2, sigma 2s2, sigma star 2s2, then sigma 2pz2 will come. Okay, then we have pi 2px, pi 2py 2, right? Now we have pi star 2px, okay, and pi star 2py. Now if you see till this one we have filled 14 electrons. 2 more electrons are left, 15 and 16. So for oxygen total electrons is 16. So if you want to fill the last 2 electrons, you have to fill like this. Okay, you cannot fill 2 electrons in one orbital. It has to be like if the orbitals are degenerate, then all the orbitals should be first filled before starting the pairing up, right? So we'll get 2 electrons here. So there is unpaired electrons, and as a result of which this molecule will become paramagnetic. And you can calculate the bond order using the same formula. Okay. Okay, so we have completed chemical bonding. Again, if I want to tell what are the most important topics that you have to revise, that is your Vesper theory, very, very important, molecular orbital theory, and then calculation of formal charges. And then you can practice Lewis structures, how to do, but not many questions are asked from here, right? So just focus on molecular orbital theory, Vesper theory, and formal charge calculation. Okay, the key important things. Okay. Next, coming to the next chapter, which is very, very easy chapter, that is your classification of elements and periodicity in properties. Let us quickly revise this chapter. Some very, very basic things about periodic table we have to understand. So what we will understand first here, what is modern periodic law, how to write the IUPAC nomenclature for elements with atomic number atomic number greater than 100. Then classification of elements, and then periodicity in properties. Okay, so first one is according to modern periodic law, the functions of an atom depends on the atomic number. Okay, it is not on the atomic mass. According to Mendeleev law, it was according to according to the Mendeleev's law, the properties depend on atomic mass, but according to modern law, the properties depend on the atomic number. Next is the why there is periodicity, because there is a similar configuration repeated over the time. And then there is in modern periodic table, it is based that the elements are arranged in the increasing order of their atomic numbers and not in the increasing order of their atomic masses. And next we have that there are 7 periods and 18 groups. N is the principal quantum for the outermost shell, and that tells which group the element belongs. And we have same number of electrons is present in the outer orbitals to find the electronic configuration. Okay, so these are some basic things you should know. 7 periods and 18 groups are present. Now coming to how to write the nomenclature of numbers greater than 100. For example, there is an atomic number of 103, right? So for 1, what is the name? That is un. Okay, for 0, what is it? Nil. Okay, and then for 3, it is tri. So U, N, and for 3, so the symbol will be U and T. Okay, like this questions you can just practice, very easy thing this one. Okay, now coming to the classification. So periodic table has 4 major groups, S block, P block, D block, and F block. So S block is your from NS1 to 2 is the electronic configuration, right? And they are generally metals. Okay, and so here what should be the, one second, yeah, this should be generally metals, and which elements they belong, they contain your group 1 and group 2, right? Next you come to P block elements. The general electronic configuration is NS2 to NP1 to 6. They are generally metallites and non-metals, but some of them are also metals, and they consist of group 13 to group 18, 1 to 2, and that's it, 13 to 18. The middle part is your D block elements, which has a general configuration of N-1D 1 to 10 and NS 1 to 2. Here, this is next we have, they are generally metals, and we have group 3D series, 4D series, and 5D series, and they contain 3 to 12 groups. Okay, so you can see 1 to 2, then 3 to 12, and then 13 to 18. Okay, next coming to your F block elements, N to N-2, F1 to 14, NS2, N-1 P6, and N-1 D0. This is there for, this is for your 6th and 7th period. So these elements are generally radioactive, and we have 2 series, 4F series and 5F series. Okay, so this is general classification of the periodic table. Now we will quickly go to the atomic properties or periodicity in the properties. First one is the atomic radius. Very simple thing. It decreases from left to right along the period. It decreases and it increases down the group. Okay, effective nuclear charge increases, so size decreases along the group. New cells are added, so size increases. Now what happens if you see in 3D series, this is given about 3D series, we have already discussed. So there is slight decrease from scandium to manganese because the effective nuclear charge is more dominant. Then iron to nickel, it remains constant because both the effects balance each other. And then if you see from copper to zinc, the size increases because the shielding effect is more than the effective of the nuclear charge. Okay. Now so in the lanthanide series, what happens? There is a steady decrease in the size. Why? Because of lanthanide contraction due to the poor shielding of 4f orbitals. Okay, so you need to remember these two important things. Now coming to ionization energy. So ionization energy increases along the period and decreases down the group. Okay, now what are the factors on which the ionization energy increases? Atomic size. If the size is small, ionization energy will be more. Effective nuclear charge is more, ionization energy will be more. Penetration effect of the orbitals. So s orbitals are more inside the nucleus. So if you want to remove the electron from 2s and 2p, more electron energy will be required to remove from 2s because they are more penetrated or entered towards the nucleus. Then shielding or screening effect. If the shielding effect is poor, then ionization energy will be more. If shielding effect is strong, then ionization energy will be less. Then stability of half filled and fully filled orbitals. So if there is any half filled or fully filled configuration, then ionization energy increases. Okay, so like for example, if you see nitrogen and carbon, nitrogen and oxygen, right? What is the electronic configuration of nitrogen? 1s2, 2s2, 2p3. For oxygen it is 1s2, 2s2 and 2p4, right? Size is decreasing, oxygen is smaller than nitrogen along the period. So according to size, this oxygen should have more ionization energy. But you can see nitrogen has half filled electronic configuration, as a result of which the ionization energy of nitrogen is more than that of oxygen. Okay, so this exception you can remember. Same applies for phosphorus and sulfur. Now next one is your electron affinity. So electron affinity increases along the period, the tendency to attract electron. As the size increases, effective nuclear charge increases, so the tendency to accept electron increases and decreases down the group. Okay, now factors affecting here is again atomic size. So if atomic size will be less, more nuclear charge, more electron gain enthalpy or electron affinity will be there. If effective nuclear charge is more, then also more attraction will be there. Shielding or screening effect. If screening effect is poor, nuclear charge will be higher and the electron affinity will increase. Now coming to electronegativity. So in same as electron affinity, increases along the period, decreases down the group. Okay. Now what are the factors affecting here? Again atomic radius, effective nuclear charge, oxidation state, hybridization. So what is hybridization? More is the s character. Okay. More s character, more electronegative. Okay. Now for example, if you see sp3, sp2 and sp. So here 50% is S, right? Here around 33% and here around 25%. So more S character, so that is why the electronegativity of sp will be, carbon with sp hybridization will be higher. Okay, fine. So yes, so this was the complete inorganic chemistry that we have discussed. Questions, like you can easily expect 12 to 15 questions from these topics. Revise them thoroughly, note it down and do some questions from this. So I hope you have found this video very helpful. Just it's like one day, just take it and watch it completely and note down all the important points, all the exceptions, all the trends, and deblock what are the properties, physical properties, what are the reactions, preparation method. So just note down it everything and revise in 2-3, like 1.5 hour, like 2 hours, and the complete inorganic chemistry will be revised. So I hope you have found this video very helpful. Please like, share and subscribe our channel for further updates. And the PDF of this inorganic revision, the all notes will be available in our WhatsApp channel. The link of the WhatsApp channel will be there in the description section. So download it, revise it and then go for the exam. Hello students, welcome back to our channel Diksha Karnataka. So as you know, organic chemistry has a very vast syllabus which includes a lot of name reactions. So in this video, I'll be discussing some very important name reactions for your KCET 2024. So these name reactions are those from where most of the questions are asked. So it's like before starting this video, I want you to all keep your notebook and write down the name of these reactions and prepare them. Okay. So let us start with this first name reaction, that is aldol condensation. It is a very, very important reaction and many one questions you will get from this topic. Okay. So first of all, whenever you are writing now, you should like 3 important things you have to remember for every name reaction. First is what is the reactant. Okay. Next is what is the reagent. Okay. And then what is the product. Whenever you revise also, like suppose aldol condensation is there, you should revise what is the reactant, reagent and product. So when you write, you need not write this sentence for note making. For note making, you have to only write aldol condensation, reactant, okay, then reagent and then product. Okay. These three things, if you make a note of all the important, some around 20-22 reactions are there, and then you have to write this reaction also. Okay. So you will make a name of the reaction, these 3 points, and then this reaction. Okay. That is how you are going to start this whole name reaction series. So coming to first aldol condensation, here you have to order the reactants 2 carbonyl moieties. Okay. So this can be any aldehydes, it can be 2 aldehydes, okay, or it can be 2 ketones, okay, or it can be aldehyde plus ketone, anything, okay. This can happen. Another condition here is we should have one alpha hydrogen. That also you mentioned here, if any special condition is required. So presence of alpha hydrogen is required. In presence of what is the reagent now? So reactants are 2 carbonyl moieties, reagent is dilute NaOH, and then what is the product formed? The product formed is beta hydroxyaldehyde or beta hydroxyketone. Okay. Now after this, so I'll be explaining this reaction now. If you have, see how to write the product easily. Okay. So if you have this one RCOH, okay, RCOR, and another is RCOH. Okay. Now this is R1, R2 and R3. Now you have to see this alpha carbon should have one hydrogen. Now this carbon should be connected to this carbon. Okay. The alpha carbon of one compound is connected with the carbon of the other compound. Now this one will go here and this will become OH. So what is my structure now? R1COH. Okay. R1COH. Here we have R2. R2 is connected. Here we have R3 and COH. Now if we produce heat, there will be dehydration and we will get alpha beta hydroxy aldehydes or ketones. Okay. So I hope this reaction, I will not be reading the whole statement. I'll be telling you the reactants, reagents, products and the mechanism if it is important. Okay. So aldol condensation, very, very important. Learn this trick, how to write the product, and these 3 things you mentioned. Then you can just write down an example. Now going to the next question, carbyl amine reaction. So what is this importance of this reaction? It is used as a test for primary amines. Okay, only primary amines will show this reaction. Again, we will be seeing the 3 important categories. First is your reactant. So the reactant is a primary amine. Okay, so this is my reactant. Then what is the reagent for this one? So when primary amines react with CHCl3 in presence of KOH, they give you isocyanides. Okay, that is carbylamine reaction. So CHCl3, chloroform and base are the reagents. Okay, and isocyanide is the products. So please write in this session, give the heading carbylamine reaction, then 3 important points: reactant, reagent, product, and then you can write down the reaction. One important point about this is it is a test for primary amines, and this one produces a foul smell. Okay, clear? Now going to the next. Cannizzaro reaction, again very important reaction. Cannizzaro reaction is a chemical reaction that involves a base-induced disproportionation reaction. So here what is the key word? It is a disproportionation reaction of 2 molecules of a non-enolizable aldehyde. What is the meaning of this non-enolizable aldehyde? Means it has absence of alpha hydrogen. Okay, to yield a carboxylic acid and a primary alcohol. So what is my reactant in this case? We'll write again 3 points. Reactant you have to write aldehydes without alpha hydrogen. Okay, this is my reactant. Then reagent is your, it's not mentioned here, you can write down concentrated alkali medium. Okay, you can take NaOH, KOH. So reagent is concentrated NaOH. Okay, then product will be carboxylic acid plus primary alcohol. Okay, now you can see this example here. We have taken benzaldehyde, right? This is benzaldehyde. This carbon is alpha carbon. Sorry, this carbon is alpha carbon. Here there is no alpha hydrogen. So this compound can undergo Cannizzaro reaction. Now this one will form, one compound is your oxidized product, another will be a reduced product. So this one will be getting converted to acid, that is oxidized product. This one will be getting converted to alcohol, that is your reduced product, right? So this is also very important name reaction. Now let us go to the 4th one, Clemmensen reduction, again very important one. So the Clemmensen reaction is a reaction that is used to reduce aldehydes or ketones. So what is my reactant here? Aldehydes or ketones. First point, reactant, aldehydes or ketones. 2 alkanes. So products is alkanes. And what is the reagent here? Hydrochloric acid and zinc amalgam. Okay. So I don't think nothing to explain here. You have a aldehyde or a ketone group. When you treat with zinc amalgam and HCl, this gets converted, reduced to give you 2H, and the compound becomes one alkane. So again, 3 points you write down, and these 3 reactant, reagent and product. So now let us go to the 5th reaction. Itard reaction, again very important one. Okay. So Itard reaction is a chemical reaction that involves the direct oxidation of aromatic or heterocyclic bound methyl group. Okay. So we should have a compound, aromatic compound with a methyl group. Okay. That is the reactant. Okay. Now what does it do? It changes this compound to aldehyde, and what is the reagent here? Chromyl chloride. Okay. Again 3 points you will write. Reactant is, you can just write down toluene, that will be easy. Reagent is CrO2Cl2. Product is aldehyde or benzaldehyde. Okay. Very important. Next, Finkelstein reaction, important reaction from haloalkanes chapter. Treatment of primary alkyl halides, okay, with an alkali metal, for example KFKI, leads to the replacement of hydrogen via an SN2 reaction. So you can write down here the reactant. Reactant is RCl or RBr. Okay. Product is RI. Product is Ri, that is for iodoalkanes, and the reagents used are Ki in presence of acid. Right. So very simple one. So mechanisms are not important. You must remember the reagent, reactant and product. Okay. That's why I'm going in this way. Mechanisms here, SN2 mechanism you can know, but it's not required for the exam point of view. Now coming to the next one, Friedel-Crafts alkylation reaction. So this is also very common reaction. What is the reactant here? Aromatic compounds are the reactant. Then what is the product? Alkyl group getting attached. What is the reagent? In presence of anhydrous aluminum chloride. Okay. So you can see here, if you have any benzene group and you can take any RX, for example CH3Cl, right, in presence of FeCl3, or you can also take AlCl3, any Lewis acid. Then this CH3 will get attached on this carbon. So this is my, again CH3 will get toluene, right? So alkylation part. Now here one more reaction I'll add, Friedel-Crafts acylation. The same thing will happen if you take here another acylation group, that is CH3COCl. Then in the product we will get COCH3. Okay, done. Okay, so 7 reactions are completed. Next one, Gabriel phthalimide reaction. This is very important. Here what is the chemical reaction that transforms the primary alkyl halides into primary amines? Okay, so this one, understand, we have primary alkyl halides getting converted to primary amines in the presence of phthalimide. Okay, so here first of all, just you can see this reaction little in detail. This is a structure called as phthalimide. Okay, when you take KOH, it is a base. What it will do? It will abstract this H and we will get N minus and K plus. Now our reagent is ready. Rx is the reactant. So R will bound here and X will be taken away by K. So we will get this NR product. Okay, now to this NR product, if you hydrolyze it, it will break here and we will get RNH2. Okay. So here one more condition is there that you have to remember. This method can only be used for the preparation of primary amines. Okay. Even you cannot prepare aniline with this method. Aniline cannot be prepared using this method. Okay. So next is Gattermann reaction. Again an important name reaction. So here the reactants are benzene disonium chloride. So if you write reactant is benzene disonium chloride. Okay. And then for reagent is copper powder in presence of corresponding halogen acid. Suppose you want to prepare chlorobenzene, then you have to take copper with HCl. If you want to prepare bromobenzene, then copper with HBr. Okay. So that is why it is a corresponding halogen acid you have to take. So reagent is, you can just write down copper with HX. Okay. And then product is haloarenes or halobenzenes also you can write down. Right. So you can see here, this is benzene disonium chloride, N2 plus and Cl minus. Then we have copper plus HCl. So this Cl will be replaced with this one. Okay. So next, Gatterman-Koch reaction, this reaction is there in the preparation of benzaldehyde part. So here what is the reagent? First is reagent is benzene. Okay, reagent is reactant is benzene. Then reactant we have COHCl in presence of AlCl3. Okay, so this one will create this benzaldehyde as the major product. Okay, so this is no other conditions are to be remembered. So first you have to remember benzene is the reactant, anhydrous aluminum chloride, then carbon monoxide in acidic medium, these are reagents, and benzaldehyde is the product. So you can only remember carbon monoxide, that is also okay, you can do with this much. Okay, now coming to next question, Reimer-Tiemann reaction, another important name reaction. So in this what happens, the reactant is phenol. First reactant is phenol, then we have reagent. Reagent is important, CHCl3 in presence of KOH or NaOH you can take. Okay, and the product formed here is, we will get OHCHO. This benzaldehyde formylation takes place. Okay, so Reimer-Tiemann reaction is the chemical reaction that is used for orthoformylation of phenols. Formylation is adding a formaldehyde group in the presence of CHCl3 and KOH. Okay, now here one more thing you have to remember, that is often asked, what is the intermediate formed in this reaction? Then it is dichlorocarbene. Okay, this intermediate is formed. Sometimes we can get a question from this part also. So the intermediate formed in this reaction is called as dichlorocarbene. Okay. Next reaction is Rosenman reaction, another important one. So here again, what is the reagent? Reactant is acyl chloride. Okay, acyl chloride. So here we have RCOCl, and reagent is hydrogen palladium barium sulfate. So very simple reaction, just remove the chlorine and replace it with hydrogen, right? So it is a preparation method for aldehydes. So we can check here, acyl chloride is the reactant, aldehyde is the product, palladium barium sulfate, hydrogen, okay, in presence of hydrogen is your reagent. So next one, Sandmeyer reaction is very similar to your Gatterman reaction. So Sandmeyer reaction is a chemical reaction used for the synthesis of aryl halides. Gatterman is also used in that case. So from diazonium salts using copper salt. So there's a difference here. In case of Gatterman reaction, we used copper with HX. Okay, and in case of Sandmeyer reaction, you can use directly CuX. Suppose you want to replace it with chlorine, you can use CuCl2. You want to replace with bromine, it will become CuBr2. Okay, so that is the difference here. So reactant is benzene diazonium chloride. Then we have CuX based on which halogen you want to add, and then we have the product here. Okay, haloarenes are the product. Next, okay, Stephan reaction. This is important one because amines chapter. This is one of the major methods of preparation for this one. So we have first reactant is your nitrile group. Okay, reactant is nitrile group. Reagent is tin chloride in acidic medium. Okay, then if you do further hydrolysis, we will get aldehyde. So major product that you have to remember is the main product formed here is aldehyde from nitriles. Now, so you can see here, this is the nitrile part. Okay, then when you do this SNH2HCl, it get reduced. Then hydrolysis will give you aldehyde. Okay, next, Schwartz reaction. This is Finkelstein and Schwartz reaction, both are important reactions from haloalkanes chapter. So Schwartz reaction is used for preparation of fluoroalkanes, right? Fluoroalkanes. So first of all, alkyl chlorides or alkyl bromides should be the reactant. The reagent can be AgF, HgF, any metal fluorides, and the product formed will be alkyl fluorides. Okay, so you can see CH3Br in presence of AgF. CH3Br in presence of AgF will give you CH3F plus AgBr. So this Br is replaced with this fluorine. Okay. Next, Williamson ether synthesis, very important reaction. In ethers, we have two important concepts. One is Williamson ether synthesis, another is cleavage of ethers. So in this, what happens? One is your alkoxide ion. So there are two reactants. One is alkoxide ion and another is haloalkane. Okay, you can take any haloalkane. So here the condition that has to be remember is this haloalkane should be a primary one. Okay, the reaction will not occur if you take any secondary or tertiary haloalkanes. That has to be primary, and then we have displacement reaction, and we get ether as the major product. Okay, so what should be there? Primary alkyl halides and alkoxide are the two reactants to give you ethers. The mechanism of the reaction is SN2 reaction. Okay, now next, Wolff-Kissner reduction, very important for aldehydes and ketones. So ketones or aldehydes get reduced in presence of hydrogen, that is NH2 in the basic medium. Okay, so reagent is, we have hydrogen, that is NH2 in presence of KOH. Okay, so the point you have to remember is this reaction takes place in basic medium, and then we get the made product formed will be alkane. So as you can see in this example, this is the ketone group or carbonyl group. In presence of hydrogen, two hydrogens are removed and this H get attached in this carbon to give you alkanes. Okay, so this is reduction. We call it reduction because here removal of oxygen and addition of hydrogen takes place. So now next reaction we have is Woods reaction. So in Woods reaction we have two alkyl chlorides you have to take, and the reagent should be sodium in presence of dry ether to give you RR. Okay, so what is the use of this reaction? This is used to prepare higher alkenes. When suppose you have taken ethane and you want to make it butane, then you can use this Woods reaction. So it always gives you a carbon more than the initial reactant. For example, you have CH3Br and you treated it with Na ether. So this part, R part will get doubled. So we will get CH3. Okay. Now suppose you have taken with ethyl bromide, then there are two carbons here. In the product we will get 4 carbons. So whenever there is a conversion of higher alkanes, you can think that Woods reaction can be helpful. So another thing that you have to remember is sodium metal has to be used and 2 alkyl halides has to be used. Okay. In Woods reaction, both the alkyl halides are same. Okay, now we have Woods fatigue reaction. This is very similar to the Woods reaction, but here you can take one. Sorry. So here you can take one RX, which is your haloalkane, and another R-X. This one should be haloarine. Okay, that means one aliphatic compound and one aromatic compound you can take. Then this R and R- can combine to give you RR-. Okay, so here it depends on which number of carbons you can take. So you can get any number based on RX and R-X you have taken. Now again the reagent is same here, sodium metal in presence of dry ether. Okay, so next reaction is HBZ reaction. So this one, in this reaction we have first of all, the reactant should be a carboxylic acid group. Okay, one important thing that you have to remember for this, it should have alpha hydrogen. Okay, so what this reaction does, it replaces the alpha hydrogen with a halogen group. Okay, so if there is no alpha hydrogen, the reaction will not happen. For example, if we have this compound CH3, CCH3, suppose we have this acid, this is alpha carbon, it doesn't have any alpha hydrogens, then we cannot do HBZ reaction in this case. Okay, so there has to be at least one hydrogen, one alpha hydrogen for the reaction to happen. Now in this case we can get this reaction. So what basically happens in this reaction, as you can see, this is the functional group, this is the alpha carbon, it has 2 hydrogens. Now the reagent is bromine in presence of PBr3. So bromine will be added with one of the H. So here one hydrogen is replaced with bromine. So what are the reactants here? So reactants are carboxylic acid, reagent is Br2 PBr3, and the product is your alpha halo carboxylic acid. Okay, so this is also important reaction. Next we have Hofmann bromamide degradation, very important reaction for the preparation of amines. Okay, and this reaction is also only for the preparation of primary amines. There is another important point with this reaction is the reactant and the product. Suppose in the reactant there are 5 carbons, in the product there will be 4 carbons. 1 carbon gets reduced. Okay. So what is the reactant here? We have to take any amide group. Okay. Amide group is treated in presence of X2, any base and water, and then if you heat it, this part, okay, this part is removed and we will get RNH2. Okay. So primary amines alone can be synthesized from this method. So we can just see this statement here. Amide reacts with bromine and an aqueous solution of sodium hydroxide, that is Br2 and NaOH, which produces primary amine. Okay. So this is a degradation reaction as the primary amine in the product has 1 carbon lesser than the primary amide. Okay. So that is because this carbon CO group is removed, so 1 carbon less. Okay. Now let us see the next reaction, Coles reaction. So this is also important one. We have first of all, phenoxide ion is the reactant in which it reacts with carbon dioxide to form orthohydroxybenzoic acid. Okay. So let us see the mechanism here little bit. First of all, phenol is there. When you treat it with NaOH and CO, this ONA is there and then CONA replacement happens. Then if you just do hydrolysis H+, you add OH and COH. Okay, so this compound common name is very popular. Please remember its common name, that is salicylic acid. Okay, fine. So these were some very important name reactions from all the organic chemistry chapters. So as I told you, please remember mechanisms are not important, but you can remember the reagent, reactant and product, okay, for all this. So if you have found this video helpful, please like, share and subscribe our channel. Thank you so much.